All right, let's understand how can you build a platform like Replit end to end. We'll kick things off with a more beginner friendly approach and eventually move to a more production ready advanced approach of building something like Replit. Let's get right into it. First, if this is the first time you're coding, this video is probably not for you. Some good prerequisites to have are basic coding. If you've done some data structures and algorithms, if you're able to write for loops, you should be fine. If you know Node.js, it's good because most of the code we'll be writing today will be in Node.js. That said, if you want to just understand function calls, you don't need to know the syntax of Node.js. You should be fine, even if you don't want to dive into the code. If you just want to know the system design, then the video should be fine. If you want to dive into the code, you'll need to know a little bit of Node, specifically JavaScript. Good to haves. If you know containerization, Kubernetes, or any auto-scaling constructs of a cloud, it's good to have. If you don't know them, I'll be explaining a few of these as time goes by. These are anyways required in the advanced section. The first approach, the beginner friendly approach, only requires these as the prerequisites. What we will learn, we'll understand some basic and advanced things by the end of it. What is something you can take away from the video? Number one, understanding how backend systems communicate with each other. What even is backend communication? Containerization, isolated environments. How can you take someone else's code and run it on your servers in an isolated environment? Remote code execution, allowing other people to run their code remotely. And lastly, the system design of building something like Replit. Some advanced things you might be able to learn from a very high level, if I'm being honest, would be Kubernetes, something called pseudo terminals, and Nix, a new technology that even I wasn't aware of up until a week ago. Before we start, a big disclaimer. We'll be going through three approaches. The first approach and the third approach will be going into the depths of. The second approach, I will explain and share why I went with the final third approach and why this is a decent approach, but not great. The beginner friendly approach, the very first approach, is how I would implement it from first principles back in college. What do I mean by this? I mean, if I did not know what containers are, if I wasn't able to gauge how difficult it would be to build a platform like this, the hackathon friendly approach I would take to build something like this. Highly insecure. So basically, if you use this in an interview, you'll get rejected upfront. There are very basic things that this approach misses. But why are we going through this approach? To make sure if you've done very little coding, how should you approach this problem? How would you build intuition to building a platform like this? Good to know what's happening under the hood, which is why we're building it, and doesn't scale very well. So don't post about Twitter on this approach. If you've coded this specific approach, keep it to yourself. If you want to show it off in some hackathon, feel free to, but this is highly insecure. Would not recommend coding this way. Great to build intuition though. The second approach would involve using what are called some auto-scaling constructs in clouds. Basically, a platform like this needs to scale very well. If 100 people hit your website, the way this platform scales is much different from how a Facebook or a Swiggy would scale. There are a lot of challenges in scaling a platform like this, which is why the second approach would use auto-scaling constructs, which basically let you scale your infrastructure. Specifically, the popular ones are auto-scaling groups, if you've heard of them in AWS. This is a mid approach, which means it's not great, but not bad either. Great for a new startup because it is secure. It is scalable. There are some downsides to it, which I will come to when we reach this section. But this is an approach I would take if this is the first time I'm building a platform like this and I have to build it really quickly. I don't have the time to get into the third approach. If I feel this approach is too complicated, this one just works. Lastly, what's called the cloud native approach, which basically means you can run this code on any cloud. You're not restricted to something like AWS or GCP. This is a good approach. It auto scales. It is secure. And this is how I would build Replit today using Kubernetes. What is Kubernetes? We will get to when we reach that slide. Let's see if the editor edits the sneeze or not. All right. What do I think of this architecture? देखते हैं edit किया कि नहीं. How did I think of this architecture? How did I arrive at this architecture when I thought of solving this problem? First principles, I've done a bit of coding. So I've thought about this randomly on nights, at least if not this big of a problem. I've thought about building something like lead code many times, which the challenges that come in building something like this are very similar to the challenges that come in building something like Replit. So I had been pondering on the approach for many months now. Reverse engineering Replit. So I spent around 3-4 hours just going through the Replit platform and monitoring all the requests that are going out. Specifically for Replit, when you go to the platform and run some code, you can actually explore their file system, explore the VM, see the processes that are running, see the mounts that they have, and you can get a lot of information as to how they might be running their systems internally. You cannot do this for other websites, but for a LeetCode or for a Replit, or more specifically just for a Replit-like platform, you can actually reverse engineer it pretty well because you're allowed to run code on some of their servers. Lastly, going through their blog posts, YouTube videos, and GitHub, thankfully they've open sourced a lot of their work. In fact, their previous approach of doing this, they now use Nix, the technology that I was talking about. But before using Nix, they used to use Docker. And this approach is actually open source on their GitHub. A bunch of other good platforms that they've open sourced is something called Rust.py, which stands for a Rust-based implementation of pseudo terminals. All of this code basically pointed me into the direction of how they might have built systems like these. I, of course, don't have access to the code, but thankfully the team has open sourced a lot of the work, so you can actually look at their GitHub and try to figure things out. This specific project also will give you a lot of information if you want to understand how their systems are working, because this is a client for talking to their systems. So if you look at the APIs here, you can understand their systems slightly better. All right, now let's get into what we're building. Let's try to explore the platform a bit and understand what Replit exactly does. All right, so after you sign up or log into Replit, this is what you see. You're given a button called Create REPL that lets you start an environment in any stack of your choice. For example, Python, Node.js, C, C++. If I search for React here and select a React JavaScript environment and click on Create REPL, it creates an online coding environment for me. It's basically a place where I can look at all of the files in my React project. For example, if I click on source/app.jsx, I see a app.jsx file that I can edit. This is basically a very basic React application. If I click on run over here and wait for a few seconds, you'll notice that it has hosted this website for me somewhere. In fact, I see something called the shell right here. And if I press the ls command, I can see all of my files somewhere else. The key thing to know here is all this code that you see here, it does exist in my browser, but it also exists on a machine somewhere else on the internet. This is me accessing that machine, and this code, this website that's also finally hosted somewhere. If I click on new tab, you will see it's hosted on the internet. It's not running locally on my machine, which comes to tell you, okay, all of this code of mine that I've been running locally over here is not actually running in my browser. It's running in some Replit machine in the US, in Mumbai, and I can access that machine from here. It's basically given me access to a remote machine where all of this code runs for me. More practically, if we want to understand through slides, what we're building is an online IDE for long running backend and frontend applications. The key here being long running. When the user comes to your platform and click on this run button, until they click on stop, they want their website hosted. They want you to give them access to a shell where they can run various commands. This is slightly different from how LeetCode works, where in LeetCode, you don't necessarily need a resource for the user somewhere. You don't necessarily need to host their code somewhere. When someone comes on LeetCode and submits some code, that code reaches a LeetCode server, runs there for a few seconds, and then the user gets back the response. This server doesn't need to continuously monitor and run the code, versus on Replit or an online IDE that lets you run something like React or a backend Node.js server. Until this process is running, there is a VM that's running the user's code, and it's a long running process. More practically, the things that we can call functional requirements for a platform like this is an online IDE for running long-running backend and frontend applications, the ability to start a fresh environment in various languages. It could be Rust, it could be Go, it could be Python, Node.js, React, whatever that specific platform supports, which as you can see, Replit supports 1,000 different stacks. You need to support them. Ability to auto-scale servers with users. The beginner-friendly approach that we will use won't auto-scale, but the goal is eventually what we build is something that can handle spikes. If there are 20 users initially and then 50 users come, your server should be able to scale up very well. Why am I talking such small numbers, 20 and 50, compared to millions that might come to a website like Swiggy? The answer is the way to scale a website like Swiggy or a simple social network is significantly different from a platform like this, where you're giving the user access to some resource for a long time. So we'll see what the challenges are that come, but auto scaling a platform like this is much harder than auto scaling a platform like a basic social networking application. Run the code in an isolated environment. The last thing that's sort of key to do here is to make sure you run the user code, you run whatever the user provides you here in an isolated environment. Let me share a small example of what I mean. As you can see, and I told you, you have access to some machine of Replit right now. If I run ls here, it lists all the commands or all the files here. If I run rm star or rm-r star or a bunch of RNS commands here, basically the command that I ran was this, pretty much deletes everything from this server. Only a few files are left. If I delete rm-r-src, it deletes the source folder. You can basically bonk the server of the user, run extremely bad commands here. What are these extremely bad commands? You should go back to the video that I shared initially, where I went to a platform like this, ran a few commands in such a terminal and was able to see their database secrets, things like these, which is not great. Though you have to be very sure when you're building a platform like this, it's running in a very isolated fashion. Whatever you're giving the user access to, that access is extremely restricted. That is what isolated environment over here means. All right. What we are not building is a very clean UI and things like authentication. Of course, Replit has 10 different things today. It lets you do AI. It lets you actually deploy your application. They're slowly becoming like a pseudo cloud provider. But we're not focusing on any of that today. We're focusing on the core moat of Replit, which is allowing other people to run long running processes on their servers. With that, let's get into the requirements one more time. The user should be able to start a new environment in a selected stack. For example, they select Node.js, React, Python, whatever stack they want to work with today. They click on create REPL and then they're taken to a coding environment like this. Over here, the user should be able to edit the code, run the code, basically do all the things that I showed you on the machine. They can add whatever Node.js code they want. For example, if you start a simple Node.js REPL, over here, what is being done is I've written the code of a basic HTTP server. And if I click on run, this HTTP server should run somewhere. I should be able to access it on the internet, very similar to the React application we made a few minutes ago. All right. These are the requirements. And we'll be taking 3 approaches to solve today's problems. A few call out in case you're a startup or suddenly someone who wants to build this very quickly and needs it yesterday. You should use an external service or a code base that does a lot of this for you. You don't have to build this in-house. In fact, for a startup, it probably might make sense to delegate a lot of this initially. It does not make sense for Replit because this is the core of their business. But if you're building an educational website, if you're building whatever other use case, training website for your employees, you don't necessarily need to build all of this in-house. And one good project to call out here is a project called Code Server that lets you pretty much run VS Code on the cloud and give you access to it inside the browser. If you look at this screenshot on the right, this is VS Code running on a browser. And an open source project that lets you do it is called Code Server. So if you're building this and you need it yesterday, what you can do is run a bunch of instances of this Code Server. And then as users come on your platforms, give them access to one of these servers and let them run from their browser code in this server where you've brought up a bunch of instances of this. So the whole point of this slide is, don't over-engineer in case you're a startup and you want to build this very quickly. Don't follow the approach of building all of it in-house is all I would say. That said, if you want to build it in-house, even better. Cool. Beginner-friendly approach. Here, I want to call out a few things. The first approach that we're writing today is extremely beginner-friendly, but at the same time, not scalable and not at all secure. So it is a great way to build intuition on how you can build systems like these, but do not use it in a production system. Do not use it in an interview. Why? Here is a video by me 8 months ago where I shared exactly why this is a problem, why this was a problem in a online coding environment like this somewhere, and how I was able to get their database secrets and delete their server and actually change their UI to say Harkirat was here. by executing a few commands. So this first beginner friendly approach is almost exactly what they were doing. So do not use this approach in production. It's a great approach to show this off in a hackathon, or if you need this quickly built in a hackathon where no one would use it, maybe do it. It's also very easy to understand and build an intuition for, acha, this is how I would build a system like this, which is why we're first going through the beginner friendly approach. The callouts are, it is insecure remote code execution. Basically, someone can come to your website, execute very bad code, and take away your database secrets. Single server setup does not auto scale. So as 2, 3, 4, 5 people start to hit your servers, you will see problems. Port conflict between two users. Basically, all users run their front ends on the same server, which can become a problem very quickly. There is again no what is called network isolation. So everyone is running their code, their React projects on the same machine, which can get problematic very quickly. Terminal is extremely rudimentary. The terminal that you will finally see here that we'll build will not be as fancy as the terminal that you just saw on Replit. We'll see how to optimize this in the later section, but for this beginner friendly approach, it'll be a very simple terminal. And lastly, very ugly package management. What does package management mean? Eventually you have to support multiple stacks, right? You have to support Rust, you have to support Node.js, you have to support Golang. How we build and bring Golang code onto this machine that's going to run the user code eventually is pretty ugly in this approach. We'll see how you optimize all of this in future approaches, but for the beginner friendly approach, these are the downsides to keep in mind. Before we start understanding the intuition and the system design of the beginner friendly ugly approach, let's get into why building Replit is hard. Why is it that a system like this does not exist a lot? Replit is one of very few such platforms that let you do this. Why this is hard to build? And the answer is, number one, remote code execution. As I told you, it's very scary to allow people all around the world to write some code and run them on your own servers. So it might feel like this is very easy, but you'll run into challenges people trying to exploit your servers, running a GPU here, or running a Bitcoin mine here, or putting all their assets, files, MP4 files, movies in your machines. So you have to run a lot of checks to make sure people are not doing notorious things, because you're giving them access to your compute almost for free. If I go to this platform and click on run, I have access to one of their machines, which is not a very giving someone else access to resources like this can spiral out of control very quickly if people start to exploit your resources. The question you might have is, Harkirat, why not run this locally here? Why do we even need to send this code? Why can I not run this Golang code directly in the browser in my local machine? And the answer is, your browser cannot run C++, Rust, Golang code. Not technically true. It can actually run Golang code or even C++ code, but for this use case, and mostly you'll see it like 1% of the times people will use something called WebAssembly to run C++, Rust, Golang code. But in an application like this, that needs to be such full stack, that needs to support every package out there, every Node.js library out there. You cannot run it in the browser. You need to run it in a machine somewhere else. Long running processes. As I said, lead code is much simpler to build compared to this, because when you're on lead code, you simply send a code base over to a server and the server runs it and responds back. That's much easier to build compared to a long running process. You send some code to a server and the server needs to run it for an hour, for 2 hours, for the complete duration of while you are here. The server needs to have some resource for you ready that you can interact with through this terminal, a website that is hosted for you until you're on this page, until you click on the stop button. That's the second reason why it's very hard to build. You are giving people resources in your server fleet, and until the person is there, you need to make sure there is some resource running on some server of yours for them. Shell access inside the browser. The other reason why it's the hard bit to build today would be this section right here. Okay, inside the browser, you're letting the user run commands, and not just run commands, get autocomplete. If I go here into this shell, if I press L and press tab, I think, as you can see, it gives me suggestions. Do you mean last? Do you mean less key? Do you mean login? It's a real, terminal. It's not something pseudo that you can put together, even though that's what we'll do in the first section. But this, in the end, we need to build a full-fledged terminal that lets you do everything. which is also very hard to build inside the browser, and not just inside the browser, getting access to someone else's terminal and being able to run things like these, get these pretty colors is hard to build, and it's even harder inside the browser. And lastly, file storage, which is not too difficult, but still difficult. In case of lead code, what happens? You write your code in a single file. You can just send this code, the server runs this code and responds back. On Repl.it, you can create a fully fledged project. You can have multiple files, multiple folders, folder inside folder inside folder inside file, and all of this needs to be persisted somewhere. If you leave this project and then eventually come back, you should be able to see all of these files somewhere on this browser, which means they need to exist somewhere on the internet. That's another mildly hard thing to build. Amongst all of these, this is probably the simplest thing to build. All right, let's see how we can achieve all of these one by one using the first, I repeat, beginner friendly, but not a good approach, highly insecure, doesn't scale, has a very bad terminal. All right, keeping all of these disclaimers in mind, let's get into the first beginner friendly approach. All right, let's get into the system design of the beginner friendly approach. For this specific system, we have one very big monolith. For those of you who don't know what a monolith is, basically means we have a single Node.js process that is going to handle everything. I'm calling it the execution service or the execute service. Step 0.1. Before you even put this website on the internet, before you even let users access this, you need to do one thing. You need to have the base code of all stacks stored somewhere. I repeat, you need to have if someone comes and creates a base node application in my Replit platform, their very first code that they see here, maybe an index.js file and a package.json file, we need to have this stored somewhere. The base code base that every application starts from. For example, if I go to Replit here, if I click on create REPL, amongst the many REPLs, let's say I select Node.js and click on create REPL, the base code that reaches here, which basically includes what all files, if you look at the left, an index.js file and a package.json file, which has some default code in it. All of this needs to be stored somewhere. We need to have the base code for every stack, React base code, Rust based code, Golang base code, somewhere in an object store. What is an object store? It's basically a place where you store MP4 files or JPEG files, or in this case, .javascript files, .package.json files, anything that is not simple text, any file. If you want to store somewhere on the internet, you store it in an object store. You do not store it in a database. For example, if you look at my Cloudflare account, this is the Cloudflare object store. And if you see REPL over here, I've put some basic base code over here for Node.js. If you look at it, it has an index.js file and a package.json file. You need to do this for all the stacks that you're supporting. If you're supporting Golang, you have to have the base Golang stored here, so that whenever the user starts a REPL, you have the base code to start from. You can copy over this folder over to the user's workspace, and that's what the user starts off from. After you've done that, after you know you've created the base code for all the stacks, is when the step 0.1 is done. This is before you actually even start coding, before you even create a platform like Replit. Step 0.2 is bringing all the languages that you support onto your machine. As I said, we have a single monolith called the execute server. This needs to execute Node.js servers, Node.js code for the user, Golang code for the user, React code for the user, whatever our user supports, it needs to run over here. And for that reason, you need to install all of these packages in this machine, in this execute service, so that when we write our code, when we create a server that users hit this Mac machine, this AWS server, wherever your execute server will run eventually, if this is your execute server, this machine needs to have Node, Rust and Golang in it. This is also not a good practice. Ideally, what should happen is this machine, this Mac machine shouldn't necessarily need to install Node. You should not be running the end user's code directly here. But since this is a beginner friendly approach, the execute service will execute foreign code directly on this machine, which is why you need to have all the dependencies for the frameworks that you support already installed. Cool. So what are the two things you need to do? Number one, on S3, store all of your base code that the user can create. Number two, in your machine where you will be finally running your code, install all dependencies or install all the frameworks that you are advertising that your platform will support. Once you've done both of them is when you can start to write the code for the execution service. Now I'll be running this code locally, and as I showed you, I already have an S3 store where I've put the base Node.js code. I also have Mac Node on my machine. I have Golang installed. I have Rust installed. So I don't need to install any of these dependencies again. If you want to do the same thing locally, make sure you're installing whatever frameworks you support, which in our case, I only have Node right now. I can add more frameworks here if need be. Next up, let's look at how does this execution service work? What all things it needs to support? What are the step-by-step things that happen when a user visits your platform? Number one, the user wants to create a REPL. The first thing that the user does is, if you look at the Repl.it website, the user needs to come here and click on create REPL, select a specific framework, and then click on this button. What happens when the user clicks on this button? What does your execute service need to support? When you click on this button, a request needs to go out to your execute service, which needs to start the creation of this specific new environment. What does it need to? Number one, it needs to copy over the base code that you had in your S3 over to a new location. It needs to store कि हाँ भाई, someone has created a new REPL. We should copy over the base code so that this is their current code that exists on S3. I repeat, what will I do? I will take the user's this Node.js base code and put it or copy it over to a new place. For example, if the REPL that the user created has an ID 1, I will copy over that code from there over to here, the base code, which includes just the package.json and index.js, not anything else. These two I will copy over from where? From the base code folder over to another folder where all of my user code is available. If I go to Repl.it, as you can see, it has all my existing REPLs, right? It has all the existing code that I wrote 2 days ago, 3 days ago, stored somewhere else, which is why they're storing all of your code somewhere. When they're starting to create your application, in that place, you're storing just the base code, which in our case, you can just copy over from a different location. That's the first thing that this execute service needs to support. What would this endpoint be? This would be the create REPL endpoint. The user tells you, I want to initialize a new REPL, and you have to do a few things before you tell the user, I am done. Now you can proceed on to the next step. Cool. Next step. When the user clicks on REPL, selects the platform and clicks on create REPL, they need to be redirected to this page where they'll see a loading screen. If you remember, when we were here and I clicked on create REPL, it first says the REPL is booting over here. And then you finally reach this page. Why? What exactly do they mean when they say the REPL is booting? You'll see this for a long time. The REPL is booting. There's a loader over here. This says working. It doesn't let you do anything. It doesn't even know what your files are. It has just a simple loader here. Why? And the answer is, when you reach this screen, you need to ask the execute service, please give me all my files. Since this is an empty project, the files are just the base code. But your browser needs to ask the execute service, bro, I am just coming here either for the first time or for the second time, I don't know. So please find my code base and return it to me so that it can be rendered here on my screen. So for that, we initialize a WebSocket connection between this online IDE interface and the execute service. I repeat, we start a new WebSocket connection, which means a persistent connection from here to here so that I can send messages to the execute service now. Execute service can send messages back to me. Why? Because eventually when this starts, I will start to write code, right? I will start to run commands here in the terminal. I need to send all of these to this service slowly and steadily. If I write 3 lines of code here, these 3 lines of code should reach the execute service. For that reason, we need a persistent connection between this guy and this guy. And that is the first thing we do. We initialize a persistent connection. And when we're initializing the connection, we also tell the execute service, hey, this is the REPL ID 1 that I want to access. And the execute service then now needs to hit S3, get back all the code for your REPL ID 1 and then return it back to you. So what is the first thing I do? Create a persistent connection. And while I'm creating the persistent connection, I also tell the execute service, REPL ID 1 is where I'm at. Please get me the code base of that. What does the execute service needs to do next? It needs to hit S3 and copy over all the code base locally to the execute service. I repeat, the execute service needs to go to S3 and ask, hey, what exists in /code/1? If you remember, where was I storing all of my code here? If you go to REPL/1, here is where I was storing all my code. So where does the code for ID 1 exist? In the location REPL/code/1. So what does the execute service need to do? Go to /code/1, copy over all the files, both locally on this machine and also send them back to the user so that the user can begin to show them in the UI. Cool. There are a few nuances here, a few things that are happening. Let me take you through all of the gotchas when you're doing this. The client told you, give me the code for ID 1. You went to S3 and you copied over the complete code, which means if there were 20 files here, you copied over all the 20 files here to your local code base. But what did you send back to the user? This is a good system design interview. Did you send back all the 20 files to the user, or did you send back something else? If you look at the code of Repl.it, if I look at create a fresh React project, click on create REPL. Now the WebSocket connection is initialized. I have asked for the files. They're still loading. And then after a few seconds, the files came back. But notice something. When I click on SRC, it takes a few seconds for app.css, app.jsx, index.jsx to come here. If I open a file, it takes a few seconds before the file actually comes. What does this tell you? It tells you, you incrementally get the files from the server. You lazily get files from the server. The server doesn't immediately give you everything. It first just gives you, okay, bhai, in the root folder, there are 3 files, index.js, package.json, and then maybe a folder. And then when you click on the folder, you ask for more things, you get back more things. But in a production system, should you get all the, if there are 100 files here, should you get all of them inside your browser? No. Should you get all of them on this computer? Yes. Why, Harkirat? Why do I need all the code here? Because the user might run this, right? If they click on run, you want to run the whole project here. So you need the code completely present here. You don't need it present completely on the UI. You need it incrementally based on what screen you are in. If you're on app.css, you can ask the execute service for the contents of app.css. If you're on app.jsx, you can ask the execute service, give me the current app.jsx code. You don't need all 100 files on the UI immediately. Next up, send the file system over to the system user lazily. Step 5, let the user edit files. What happens after this? After I'm here, I will begin to change the code over here, update my application, add whatever logic I wanted to add. And all of this code base needs to reach back to both S3 and the execute service. If I write a bunch of lines of code here and then click on run, I want my front end to have all of these lines, right? So I need to send all of this over back to my machine. And how do I do that? Anytime, let's say this was the original code that I had, and I added a new line of code over here. I need to send this over the WebSocket wire, just the diff. I repeat, you should ideally send just the diff. Can you send the whole file again and ask the execute service, please overwrite this file? Yes. In fact, that is what we'll be writing in the code as well. But in a system design interview and in production, should you just send over the diff versus, sending the whole thing, the whole file? Yes. What are the benefits of sending just the diff to the server versus telling the server, okay, here is the completely new updated file? Benefit number 1 is you're sending less data to the backend. You're only sending one line versus sending all of these lines again. Okay, yellow override the data. What is benefit number 2? Can you think of this one? There's a very nuanced benefit of when you're sending diffs to the backend versus sending the whole thing. The answer is collaboration. If this editor allows multiple people to edit at the same file at the same time, which Repl.it does. If I go to Repl.it and open the same REPL in a different tab, both the people can edit the same file. I can edit app.jsx here, and my update comes here as well. If I was sending the complete thing to the backend, then their changes will override each other if they're writing at the same point. But if they're just sending diffs, then you can support collaboration. You can support, okay, browser number 1 will send their diff, browser number 2 will send their diff, and then you can reconcile them on the backend. Is this easy to do? Sort of. This was my GSOC project back in 2016, where there was an online IDE like this and I added collaboration to it. It's out of scope for this video. But one of the reasons why you want to send over just the diff and not the whole file. Once this change reaches the server, what does the server need to do? It needs to, number 1, update the local file system. Okay, this extra thing was added. Let me add it here as well, so that in the end, you are editing code here, but your changes that you're doing here are reaching the final system as well. If I do a cat of app.jsx here, which basically just prints the contents of that file on the server, you will see the changes that I'm adding here are very quickly reaching the server. Did not reach and did reach. So if I write hi there here, and if I run, I see hi there here as well. So the local changes that I'm making are reaching the Repl.it server, which is why the code change that has reached there, number 1 needs to be propagated here to the file system, which is what you exactly saw. Number 2 slowly needs to go to S3 as well. You want if the user eventually leaves this platform, closes this window, then this VM will also stop after like a minute or 2. You want their changes to be persisted in S3. So the final place where I'm storing the user's code, for example, index.js and package.json, if the user is making a change here, initially it only needs to hit and reach this file system. But eventually, before this VM dies, it should slowly be pushing code to S3 as well and backing it up, so that when the VM does die, when let's say the user leaves and the VM dies, your changes reach the final S3 location and they are permanently persisted over there. A few callouts: when you're sending data from here to S3, you should debounce it. By debouncing it, I mean, if you get a lot of code changes from the user, let's say the user sends you 20 different code changes together, you should maybe batch them together and store them together in S3. You don't need to one by one overwrite the S3 files. Number 2, you can also mount a directory to S3. So S3 gives you, there's a library that basically under the hood would do the same thing, but it can let you mount a server, for example, this file system, over to S3. So you don't have to write all the logic of backing it up to S3. You can just delegate it to the mounting service, which under the hood will do the same thing for you. If you don't understand this part, it's fine. The first call out is important. You should debounce sending these code changes over to S3. You should not, shove every change that's coming here very quickly over here from the file system over to S3. All right, cool. That's all for updating the file, and the logic to add and delete files also remains the same. If I add a new file here, if I delete a file from here, pretty much need to do the same thing. Tell the execute service, hey, this thing has been deleted. The execute service will store that in the file system. The execute service will tell S3, delete this specific file. The user has deleted them. That's how you stay in sync across 3 places. Your local browser, this has the code. Your execute server, which has all your code in the file system. And then lastly, S3, which has a copy of your code in case the VM dies down and you come back to the project after a few days. Cool. All right. Step 6, the last step, I think, is actually running the code. Now you've started a project, you've written some code, and that code exists over here in your file system. Whatever code you ran has reached the file system over here. The last thing you need to do is allow the user to run a command inside this execute service, so that the user can, start their front-end or back-end application. You need to allow them to click this run button or allow them to send a command like npm run dev that actually starts their server here on the execute server. How do you do that? You again over the WebSocket wire can send ke bhai, this is the command I need to run, npm run dev, and the execute server can execute this over here. This is just a simple Node.js server. Inside the Node.js server, you can always take a command as an input and execute that command. Should you do it? No. This is where the insecurity comes out into this picture. Why insecurity? I mean, this is where the code is not secure, because you're running this command directly on this machine, which is, let's say, this execute service exists on a Mac machine. You're running npm run dev or whatever the user is sending you directly on this machine, which is what it makes it insecure. But for now, in this approach, what are we doing? We are simply running whatever the code user sends us on this Mac machine, and that will start the process locally. So by the end of it, you have something running on port 3000 or wherever your front-end application is running. And you have the execute service streaming back the logs to the front end so the user can see them here on the terminal. Cool. That's the last thing your server needs to support, which is actually allowing the user to click on the run button over here or run a command over here, for example, npm run dev, or even a command like ls. All of these are a command that you send to the backend. The backend runs that command and streams you back the logs. Ki, haan bhai, if you run ls, this is what you see. If you run npm run dev, this is what you see. All right. One more thing. When you've run npm run dev, you started the front end, right? If I go to Repl.it, and this is a simple React project that I have here. When I click on run, number one, something runs in the console over there. Something is executing on that machine. But number two, it is also exposing the front end somewhere, and I need to be able to see that front end and explore it. And how do you do that? Well, when you ran npm run dev, this machine exposed something on port 3000, let's say. You can simply tell the user, okay, bro, please visit this website on localhost :3000. This is bad for a few reasons. I'm repeating this many times. This approach is not great, but this is a good start. Why is this bad, Harkirat? You have a single execute service that is running. This is the execute service. This is running on the same Mac machine. What if two people connect to Repl.it? It's not necessary that Repl.it is restricted to a single user, right? What if I open one REPL here and then an incognito window, open another REPL? Let's say both of them click on the run button. Then what will happen on my Mac machine? My Mac machine will like, first person told me to run npm run dev. Second person told me to run npm run dev. First person took over port 3000. Second process will fail. Both the machines, both the users are running code on the same machine, which is why this approach is bad. But let's say if you only had a single user, this approach works. If you had multiple users, but they were not running code on the same port, then you will be fine. Very soon we'll see the code for this and how this actually works. That might give you a better intuition if you're confused at this point. And lastly, if the user ever disconnects, they close their REPL. You should just clean up resources here, which basically means wait for a bit before actually removing the folder. If I close the window right here, you shouldn't immediately remove this folder copy that you had locally. You should wait for a few more seconds, few more minutes. What if the user joins back? If they don't, then delete this from here. Flush all the changes to S3 in case there was something you missed, in case there is some file change that you did not do to S3, flush that over to S3. And lastly, stop any lingering processes. If the user had run npm run dev over here and that's still running, stop it because the user has left the machine. You don't need to keep running that process for that user. Cool. That's a high level of how you can build a system similar to this. I've already written the code for it. I'll show you what it looks like. What are the things that will sound and seem a little weird in the final code that we look at. Number one, the UI will be janky. I've already talked about that. Number two, the terminal. This is the important thing. Terminal will be very minimal. And by very minimal, I mean, if I go to Repl.it and explore the terminal, as you saw, if I press L and press tab, it shows me all the suggestions. Okay, do you mean this? Do you mean this? Do you mean this? The terminal that we've created right now is a very rudimentary terminal. It's just a simple input box where you can run a command npm run dev, and that gets sent to the server. When you press enter, then you get back a response from the server. Okay, this is what the output was. it doesn't yet support, the terminal protocol, which is why you cannot run npm and press tab and then hope to see a bunch of suggestions. We will do that in the next section by using something called PSTs or pseudo terminals. For now, these are the two things I'm calling out initially that will feel a little weird. This though seems like, not a good platform, not even close to Replit. The answer is yes. There are a few hacky things we have done here to get it off the ground. And then in the next section, we'll see how you can make it better. Cool. The downsides of this approach before we go into the code. I've repeated this a few times. I'm going to, call it out one more time. Do not share this approach in an interview. This is a bad approach. This is just a good intuition building approach. This is how it might work, of course, if there were no bad people in the world. Unfortunately, there are bad people in the world. You don't want to expose your applications like this on the internet. Number one, remote code execution is a bad thing. You're allowing people to run things natively on your machine. If someone sends you run npm run dev, you're running it here on the Mac machine or whatever Linux machine that you might be running your execute service on. So allowing other people, random people on the internet, to be able to run things on your Mac machine is extremely insecure, something you shouldn't do. Again, the video I've already covered why this is bad and how I was able to hack a few systems in that specific website. Single server setup doesn't auto scale. The other problem with this is everyone is on the same server. Everyone is hitting my Mac only. Everyone is starting their Node.js process. As soon as 5 people start, the process will, my server will begin to die. My single server cannot support so many users, cannot even support 5 users, let alone 50 users. Port conflict between 2 users. If 2 people run npm run dev and both the React projects start to take port 3000, there will be a conflict. They won't be able to, the second person basically won't be able to run their React project. And lastly, terminal is very ad hoc and first principles. As I said, the terminal that we will build right now is very first principles. It's an input box where you can put a command and press enter. It will send your command to the server and give you back the response, not how you want to actually build this in the real world. That's all the downsides. I think let's get into the code base now. Before we get there, also a few disclaimers. I'm using Node.js to keep it simple. You probably want to use something like Golang for this. The reason is it's very easy to run Docker via Golang or even Kubernetes. So that's my only call out as to what language might be good for building a system like this. I'm using Socket.io to keep it simple. As you saw, we had to initialize a WebSocket server. You can write WebSockets various ways. One way to do that in Node.js is using this library called Socket.io. You don't want to do this in the longer run either, but Socket.io API is much simpler. If you ever want to create a connection between a browser and a server, Socket.io makes it very easy, encapsulates a lot of complexity for you, which is why we're using it, just to keep it simple. I'll be writing code in TypeScript, but nothing too script, so keeping it fairly simple. If you don't know TypeScript, you should be able to catch along. I will not be adding any extra fluff like ESLint or Prettier or a bunch of things that you should probably have in a JavaScript project, just to keep the code very minimal, actionable, and easy to understand. Basically, try to limit the number of files that we'll be looking at. Lastly, not writing any mono repos. So if you look at the front end code and the back end code, you will see a lot of code repetition, which you should also optimize for in a better application. Should you create this a Zig based, well-linted, 100% tested CI/CD implemented system? Yes. If you're building this in the real world, you're a very big company like Repl.it, you probably want to build this, like to add hundreds of different cosmetic things that I'm not adding, just to keep things simple. We're limiting the scope of this tutorial, so we have lesser number of files to go through. With that, let's get to the code base before we move on to the better solution. Let's get into how I've built this first version of this application. All right. Before we proceed, one more thing. Let's introduce pseudo terminals or PTY once. We can still do the rudimentary approach that I mentioned a few slides ago. But I think it's just easier and almost as difficult to build a pseudo terminal. So rather than having a rudimentary place where you can, run commands, let's build a proper terminal. And for that, let's understand a few concepts. The concept that we need to understand is something called pseudo terminals, which, as the name suggests, it is a terminal that you can create, but it's a pseudo terminal. It's not a physical terminal. It does not, exist on your machine like this. For example, here is a real terminal on my Mac. And then if I ever want to not create a real terminal, but allow other people to access my machine, then I create what's called a pseudo terminal. Hopefully that makes sense, and the name is self-explanatory. If you've ever tried RDP, if you've ever tried Team Viewer in Windows, where you're trying to access your friend's machine, pretty similar. Only you don't get GUI access, you get like terminal access to that specific machine, which is exactly what we want. What you can do is create a pseudo terminal that your browser can talk to. What you can do if you want to ever, expose your machine over the internet so that other people can, visit and run commands on it, you can create a pseudo terminal and then stream keystrokes from someone else to your machine in that pseudo terminal, and then, send them responses back so that they can understand it. That's basically what a pseudo terminal is. If you ever want to, create a terminal inside the browser, which is the thing that you see here, this is a browser instance and you see a terminal inside. If you ever want to do this, pseudo terminals are probably the way to go. Xterm.js, this library that you see on the right, is a library that lets you fetch and forward keystrokes to a pseudo terminal that you can spawn on your server. I repeat, Xterm.js is just a client-side library. This thing is just a client-side library that you can run in your browser so that you see a terminal-like interface, and whatever you type over here, it converts it into the format that a terminal can understand. Then you can forward this to your backend server and you run this inside a pseudo terminal, then get back the data from the pseudo terminal, give it to Xterm here, which will render the keystrokes that the server responded back with. That's what a pseudo terminal is. What is Xterm? The library that you use on the front end to talk to pseudo terminals. The old approach that I suggested a few slides ago, what was that? That was, okay, I'm going to create an input box like this. This is sort of the code that I had written. Okay, input box like this. You write npm run dev, ls, whatever inside, you press enter. This command goes in a single go to the server. The server execs that specific command and then responds back with either all the logs together if the process exits immediately, or it streams the logs from the server and you can put them on an input box. Pretty ugly, as you can see, like not even close to sellable. And hence, let's build a real terminal. For that, now what we will do is, when the person comes to your website and creates a new shell, this is the way to create a new shell in Replit. We won't necessarily have such a clean UI, but you get the idea. In our UI, there will be a button, and when the user clicks that button to create a shell, we'll send a command to the backend server or send some data to the backend server and ask it to create a pseudo terminal. The backend server will then create a pseudo terminal. How does the backend server create a pseudo terminal, Kirat? There are many implementations of creating pseudo terminals that can talk to your machine. One of them is the one that we saw a few slides ago that Replit has open sourced themselves. So we can use that, or there is a common implementation in Node.js called Node.pty. You can use either one of these to start a terminal on your backend. And once that is done, all you have to do is relay data from this browser to the PTY and get the data back from the physical terminal to the browser. So you can write some basic code and open a terminal on the browser. How? By using the Xterm library. And this library, whenever you start to type inside, let's say you typed, this is incorrect, but if let's say you typed ls here, it will convert them into some format that your PST understands. You send that to the backend, forward it to the PST. This PST might respond back with all of this response. If you run ls, this is what you get back. And then you can forward that to xterm.js again, which will, render them inside the terminal. That's a high level of how we will create a terminal. If you want to see the implementation that I copied a lot of code from, is less than like 20 lines of code. It's this right here. It's this project on GitHub called xterm socket.io. This is my fork of it. There's an original project by this person. It gives a very simple implementation of how you can, create a browser terminal that talks to your machine. All the server code resides in this one. As you can see, it's less than 37 lines of code. We'll go through this very soon. All the client-side code resides, where does it reside? I think client.js. Yeah, here. So yeah, we'll go through this very soon. But that's how you can create a terminal to your backend server, which is exactly what people want in a website like Replit. So yeah, that's a high level. Let's get into the coding bit now. All right, let's get into the coding bit. Before that, let me show you a quick demo. So if you look at what we have in front of us is a website where you can go. It gives you a random ID. You can also change the ID if need be, and you can select an environment. We have Node and Python right now. Let's start something inside Python. And as you can see, that's pretty quick. It has a basic main.py file. If I type something here, I can actually run it. And same for Node.js. So if I go back to the landing page and select a Node.js environment, give it a random name, and click on start, it copies over code from S3, has a basic place in S3 where my code is. And then when I reach this place, it gives me all that boilerplate code. If I change any of the code right here, it reaches my machine. If I now run cat, whatever index.js here, the change that I made here has reached here, has also reached S3. And then if I run npm install, which will actually bring the node modules folder here, and then node index.js, if I click on see output, I see the final output here, which is hello. If I change this to hello world and then rerun node index.js and click on see output, it says hello world, so on and so forth. What is the problem here? The problem is, this is my machine. I don't want anyone to come and, be able to explore my file system, look at secrets, pictures, anything, weird that exists in my machine. So for that reason, never should you do this. Never should you expose your personal terminal to the world, even if they're, exploring the whole file. Eventually there'll be notorious people who, move out of this specific folder and start to explore your machine. Cool. That's what the final output is. Let's go back to the code and look at how I've written this code. It's a simple single service, so that's like nothing too complicated happening. Let's get into the actual code of this. All right. If you explore the code base, it has two sections, the bad code and the good code. The bad code has a backend and a front end. This is where we've written all our code to create the WebSocket connection, receive the file changes from the user, store them in S3, so on and so forth. The front end has all the code of, everything that you see over here. Let's start one by one. Let's see the endpoint that gets called when you click on start coding. What exactly happens then? If you open the backend code, you'll see it has index.ts, which is the top level file here. If you explore this from the top, I import a few things and in the end call init ws, which has all my WebSocket logic, and init http, which has all my http logic. If I open this function, you will see I've exposed a /project endpoint, which does what? It gets the REPL ID and the language from the user, which is exactly what's present here, right? The language that the user wants to start their REPL in, and then the ID of the REPL that the user wants to start. You should ideally add validation here, make sure the ID isn't already taken. And then we copy over the S3 folder from base/language over to code/REPL ID. If I go to cloudflare.com, you will see I have all the base code in this REPL/base/Node.js for all the basic Node.js code, the starter code for a Node.js application, and for a Python application, it's present here. This has a single main.py file. This has an index.js file and a package.json that has all your dependencies, which pretty much is nothing for this specific application. Once you have this in this folder, when a user comes and creates a new REPL, we want the base code for that specific language to be copied over here. For example, as you can see, I have a few already created. If I open one of these, it has the Python code copied over from the base folder to here. So what exactly does this endpoint need to do? Whenever the user says, I want to create a project, it needs to copy the S3 folder from base/stack, which is base/Node.js or Python, over to code/the REPL ID for that specific REPL. All right. If you want, you can dive deeper into this code base. There is also a small bounty here. But what does it do? It gets all the contents of the first folder, iterates over all the contents of the first folder, and then calls s3.copy object, which actually copies over the object from the source to the destination. That's how you copy over files from the base folder over to the other folder. I'm not diving deeper into all of these, but if you want to understand each and every part, just copy over this code, paste it in ChatGPT, and it'll explain you and maybe even solve the bounty for you, if I'm being honest. Probably decrease that. It'll basically share how this code is doing what it's doing. But if you look at it logically, we first create this thing called list parameters. Okay, what do I need to send to this list object v2 function to get back everything that exists in this source prefix, which is /base/Node.js or base/Python. And then there is some continuation token logic here, which don't worry about, but basically, you can only get certain number of files. If you have 1,000 files, you cannot get all of them together, which is why there's some logic here to make sure if you get 50 files first, and then you want to, get more files, there's some logic to, recall the function, but don't worry about that just yet, because our folders are going to have like the Node.js folder has like 2 files. So this continuation logic, even if you remove, which basically means if you remove this, as well as if you remove this continuation token here, it will still work. But I've just kept it to make it more, better if you have more code in your base folder. All right. That is what the /project endpoint needs to do. When does it get hit? If I go to my front end, if I click on inspect and click on network, if I click on the start coding function, if you look at it, is when the request goes out to /project. And if you look at the payload, it was Node.js for the language, and Repl.it is please cool. And the response that I get back is project created, which is exactly what the server returns over here. Cool. If you look at please cool, and if I go to Cloudflare, you will see REPL/code/please cool has actually been created for me. It's copied over all the basic Node.js code here. Cool. That's what the first and only HTTP endpoint does. Now, when the user comes here is when a few things happen. Let's go over that next, but I hope it's clear what the first HTTP endpoint does. All right, next up, we need to understand the WebSocket layer. Basically, if you go back to source/index.ts, we initialized an HTTP server. We also initialized a WebSocket server, the goal of which is, okay, once the user reaches this page finally, whenever user types something, that typed thing reaches the backend. Whenever the user writes something in the terminal, it's able to talk to the pseudo terminal that is created in the backend. All of this logic to relay information from the browser back to the server is done through this WebSocket layer. Let's try to understand this code slightly slowly. The library, as I said, that we're using to create a WebSocket connection is this library called Socket.io. It will exist somewhere here at the top. If you look at the ws.ts file, which exposes the init ws function, we first initialize a WebSocket server. What is a WebSocket server here? Basically a place where people can connect and do two-way communication. The browser can send things to the backend. The backend can send back things to the browser. We say anytime a user connects, anytime a connection happens, we get the REPL ID from a specific parameter. Basically, if you go to the front end and go to coding page.tsx, you will notice we initialize the WebSocket connection to some URL !room ID equal to the REPL ID of that specific REPL that the user is on, which is why we extract this REPL ID here in this variable. And then if it exists, we first fetch the folder from S3, basically bring it from S3 locally to our machine. And then we emit the loaded event. Okay, bro, I got everything from S3 and here is the root contents. What does root content mean? Okay, here is everything present in the root folder. If there are more folders, the front end can ask for the contents of those folder. If you look at the fetch dir function, this just fetches the things in the current root folder. If you look at this function, what does it do? It reads the directory and returns back a bunch of files with their type. Okay, bhai, this is the type of this specific directory. It's either a directory or a file, and this is the name of it. Does not recursively find all the files, returns them lazily. Returns them in the current root folder, and then initializes a bunch of handlers. Okay, bhai, if the user disconnects, ideally there should be what? There should be cleanup logic here to remove the files from the file system. I haven't added it, but feel free to add it. I'm adding a bounty if you want to learn it. It's not too much, like $25. Add the logic. I mean, don't put it in GPT. Do it for learning. Okay, cool. Fetch dir. Whenever the user, so let's say the user is here and I run npm install. And if I refresh the page now, I have not just the files, but also the folder now. And if I click on the folder, I need to fetch all the files inside this specific folder. So when you click here, you need to get back all the files from the server, basically all of this. If I click in any of these folders, I need to get back all the files. That exists here. Okay, whenever the front end asks the backend, ki, haan, bhai, let me get the content for this specific folder, the server fetches the file content for that specific subdirectory. So if you go here, oh no, sorry, this is something else. This is fetch content. This is fetch dir. Fetch dir simply, ki, haan, bhai, given this input directory, again find the contents of that directory. The function that is running here is the same function that was running here. This got you everything in the root folder. This gets you everything in that specific folder that you're asking for. For example, if you ask for the node module /.bin folder, that is what you will get access to here, and then you just return it back. Here, what is callback? Go through Socket.io syntax a bit. If you ever want to, send something and receive back the data in WebSockets, this is sort of an abstraction on WebSockets that lets you do it. It still uses, if you want me to go more technical, it still uses WebSockets under the hood. It's still using the same thing of, client sending something to the server sending something back. But if you use this callback syntax, Socket.io does some magic on top for you to, whenever I'm calling fetch.dir, if you look at it, I'm calling fetch.dir in the client side here. I do a socket.emit fetch.dir. Okay, whenever the user is, so this onSelect function is called on the front end whenever the user clicks on a specific folder. And what does it do? It says, if this is a directory, send fetch.dir to the server, and whenever the server responds, the control will reach here. This is a callback model in Socket.io. You can also not do this and be like, I will not do the callback logic, and rather do, socket.on whenever the server responds back with something, and, have a slightly more uglier syntax. But this is the slightly cleaner syntax. If you sort of want to do the request response model in Socket.io, you want to send a request and get back response, and, sort of, you can say in one go, it's still using WebSockets under the hood. How can you do it? You can be like, hey, this is what the function that I want to run there, or the type of my message. This is the data of my message. And this is the function that Socket.io should call whenever the server responds back with something. And what do we do on the backend? Okay, whenever the user asks for it, get the directory that they want, the contents of the directory, and then call this second function callback so that the content that we're sending reaches the user here. And that's how this fetch.dir call happens. All right. This might sound like or seem like an HTTP call because you're requesting something and then getting back a response. This looks very similar to, fetch some URL. And then once that is done, a callback URL where you get back control when the fetch request succeeds. So yeah, the syntax is similar, but under the hood, this callback syntax still uses WebSockets. All right, cool. That's fetch.dir. Fetch content. When I click on a file, I want the content of the file. As I said, we're not bringing everything in locally. We're bringing it in incrementally. So if I click on a file, the front end should send a request to the backend, give me all the contents, and then the backend should read it from the file system. If you look at the fetch file contents function, it reads the file and then finally resolves it. This is promisified syntax. You can also use a simpler callback syntax if you want. But what is this? If you want, feel free to use this as a black box as well. The fetch file content will just get the path to a file and return back the contents that you can respond back to the user. Where does this get called? If you look at where fetch content gets called, it's right here. Okay, when the onSelect function gets called, if it is a directory, then you fetch the contents of the directory. If it is a file, then you fetch the contents of that file. Cool. That's so basically when I click here or click here or click here, somehow onSelect gets called. You can look at the front end code and see how onSelect gets called. And then if it's a directory, you get back all the contents. If it is a file, you get back all the file contents, the textual contents from the server. Cool. That is fetch content. Update content. Explanatorily, if I update any content here, it should reach both the file system here as well as S3. And that's what this guy does. There are a few to-dos here if you want to fix them, and maybe I'll add a bounty as well. What does it say? Anytime the user wants to update content, we first save the file locally, which means update the contents locally, and then save it to S3. Again, there is an assumption here. Okay, we're sending the whole file. We're not sending the diffs. If you really want to optimize this, the front end should be sending the diffs. That's the first thing I've written here. But for now, we're just sending the whole file. So if I ever edit a file, the front end sends back the whole file to the backend, and then the backend, number one, saves it locally. You can look at this function to see how it does it, and then stores it in S3, which again, you can throttle a bit. You don't have to store everything in S3 immediately. Doesn't matter either way. It's like not an expensive of an operation for you to worry about, because we're debouncing things on the front end. If you type very quickly, only after some time does the update go out to the backend. Not on every key press is the backend request going out. Cool. And lastly, request terminal. This one is for when the user either clicks on plus button that opens the terminal, or we by default open the terminal for them. Whenever the user asks for a terminal to be created, so I've created a terminal manager class that, under the hood uses what? Uses Node.pty, which is one of the libraries that let you create pseudo terminals. This terminal manager's goal is, it lets other people, other functions create a terminal and then write to the terminal and then clear the terminal, which means delete it. This is basically copied from the project that I originally discussed, which is xterm socket IO. This code basically I've brought into my code base, which is why, a lot of the code that you see here is repeated. The terminal manager, if you basically want a smaller code to just understand how this thing over here happens, I would urge you to go through this small project, set it up locally and see how it works. I have just integrated this project here and like added a bunch of abstractions on top so that you can eventually allow the user to, create multiple terminals just like Repl.it does. Cool. The request terminal callback, what does it need to do? Create a pseudo terminal for the user. The terminal data endpoint needs to, whenever I start typing here, forward things to that specific PTY that you had created for that specific user. So when create PTY gets called, we create a new terminal and we set that here in a local variable. And then finally, when write happens is when we update that local variable. By write to this terminal, the user has sent us some data. In the end, if I'm typing something here, whatever I'm typing is reaching the backend, a terminal on the backend, and is being written there. And also the terminal on the backend responds back. For example, here if you see, it says term.onData, call the onData function, which basically is this right here, which sends back data to the front end. So both, whenever you have a PTY, again, you can go through this code to understand it. Whenever you're creating a pseudo terminal, the front end needs to send the keystrokes to the backend. The backend also needs to respond back with the keystrokes. I have received, if I press, ABC here, the backend responds back with I've received ABC. If I press LS here and press enter, the backend responds back with all of this. So the backend will also write data to the front end, which how we're sending back from here, the create PTY, whenever you create the terminal, the term.onData calls this callback, which calls this function, which we have defined here, which sends back to the front end. Here you go. This is your response for the create ls command. Cool. That's pretty much it. That's all you need to create this section right here. The other extra thing is this C output. This is probably a front end thing. If I do run npm run dev here, node index.js here, if I click on C output, I see hello whatever written here, because this started something on port 3000, and here I've just hard coded localhost :3000 to the iframe, which is why you see it. You can optimize it a little bit better. Don't optimize. Basically, this is as good as it gets locally. The next section we'll see how you can create this very dynamically and not hard code this URL. But for now, this is what we have: a basic version of Repl.it. The backend code, sort of, hopefully we understand. The front end code, all of this thing on the left, I got from a code pen. So let me search. I probably have it somewhere here. Yeah, so the front end code for this section right here, I've sort of copied from this code pen. I'll link it in the description somewhere. It gives you a very nice sidebar to explore, and the code here, of course, had to change the syntax a bit. Their file directory structure was a little different than mine. So yeah, you can explore that if you want. This has like a very simple API to go through. Let me show you a little bit more of how I send backend requests, how the terminal maybe gets initialized, how the code from here reaches the server. If you want to look at the front end code, most of it exists in frontend/source/coding page.tsx. This is a sort of top level component for this page. And what does it have? Does not use, so it uses this library called emotion/slide, because that's what these guys used. And then that's how I did styling all along. So I'm not using Tailwind, I'm not using MUI, I'm using emotion/styled, which is also a styling library that lets you, put CSS like this. So you can, create a new component called container and then use container, which has this CSS on top of a div. Cool. Let's look at what's the first thing it does. It gets the current REPL ID from the URL. So if the URL, if you look at it, has $REPL ID equal to something, it gets this REPL ID. So REPL ID by the end of it will become this. And then it gets the socket, the connection to the backend. The use socket hook, if you look at it, simply initializes a socket to the backend with the specific REPL ID and returns that socket. Whenever socket does exist or does get initialized is when we say by socket.onLoaded, when the backend server returns this loaded event, means it has fetched the S3 folder locally and is giving you back the root contents, is when you store the root contents in this file structure variable, and then is when you actually render everything on screen, which renders what? A button at the top right that lets you show the output, which basically means, whatever is rendered here. If output is true, then we show the output as well, else we just show the terminal. And then the editor is basically this thing on the left, and we're passing in the file structure inside this. And then inside this, I've written basically the same code that I got from here. So most of the code inside editor is brought in from here. Most of the code in terminal I've gotten from here, and then output is like a simple iframe. So a lot of the front end code is basically joined from the internet. If you go through the editor, you'll see on select gets called when you either click here or click on a file or a folder, which is why control eventually reaches here and you request the server for either the directory structure or for the content of that file. And when you do get the content of the file, you set it in this variable, which then gets propagated to the editor and then gets put over here. The terminal logic, if you want to look at it, what do we do here? We emit request terminal whenever this terminal ref changes. It's basically means this div gets initialized in this ref, and then whenever the terminal responds back with some data is when this handler gets called, which puts it inside this terminal and starts to write things here. And anytime terminal on data, anytime this terminal variable that you have created, which comes from where? It comes from extern, the library that I told you that lets you do this. Whenever you get back any data from this terminal, you emit it to the backend. So this is how you send keystrokes to the backend. If you basically put a log here, you'll see the log comes whenever I type. So if I refresh this page and start typing, you'll see whatever I'm typing, SD in the terminal is coming here. So basically whenever I type something, control reaches here and then I emit that to the backend. Whenever the backend responds with something, the control reaches this terminal handler, because I've said socket.on terminal handler, and if I log whatever here, you will see that's basically the same thing. I already had a log here, and if you do a AB2 string of data, you see the same thing, which means when I press A here, I send the server A and the server responds back with A. Whenever you're in a bash session, you'll see this is a little delayed, right? If I press L, I don't immediately see L. This is a local machine, which is why you do see it. But if you ever SSH, it takes much longer because the server is responding back with, I have received your keystroke. Here is your keystroke back. And then of course, when you have more data, server responds back with that. All of that we put here by doing a term.write. That's how the terminal gets propagated. And then npm run dev is just, running on your machine and starting something on a port or whatever node index.js, which is why you can, see the output. I have like a lingering one from the existing session, which is why I did not start, but you get the idea. Yeah, the front end code is pretty small. It's also not great. It has like some standard practices missing. So feel free to create to-dos. Happy to give out bounties, although I'm not very keen on pursuing it. Merging bounties, but as in merging too many PRs, so don't spam it. But at the same time, you feel something needs fixing, you need a lot of practice. Just make sure it's well tested and create a PR. I will review and merge. That's it for the bad code, which is like how you should not build Repl.it. In the next section, let's look at a better architecture. I've spent a lot of time thinking, looking at their architecture, figuring out what they're doing, and then came with that architecture. Let's see how close it is to Repl.it. There's no way for us to verify. I've sort of inspected a lot of their requests file system and tried to figure out an architecture, which is what we'll discuss in the next section. Let's get into it. All right. The good solution. Let's try to figure out what were the problems in the first approach, how can we fix them, and what is a new architecture that's probably closer to what Repl.it does. What we've done until now is not even close to something you should do or probably they do in production. There are two problems in the first approach. There are actually many. The two biggest one are, number one, remote code execution isn't safe. What do I mean by this? I basically mean if you're on this specific website, you can run anything here. I can literally explore Harkirat's complete code base because Harkirat is running all of this logic on his machine. I have a sudo terminal to Harkirat's machine. I can access, things in his file system, look at the secrets, do a bunch of random things that you don't want people on the internet to do. So you don't want to allow anyone to do, remote code execution or create terminal sessions with your main machine. That's the first big flaw in the approach. And what's the second flaw? The second flaw is, it doesn't auto scale. Right now, we had a very big assumption Okay, you have a single machine that is running this node index.js, and everywhere people in the world will connect to the same machine. And as soon as more than 20 people connect, your machine doesn't have enough resources to be able to connect to them. How can we fix this? What is an architecture that, number one, auto scales, and number two, makes remote code execution slightly safer? Let's get into it. The good solution. There are multiple approaches to this. There's no one better solution over the other. That said, I do feel this container orchestration solution is slightly cleaner compared to a cloud specific auto scaling solution. Let's understand what I mean by this and this. I've also written some buzzwords here: AWS auto scaling groups and ECS. And here I've written Kubernetes. Let's quickly understand what these are. ASGs, or auto scaling groups, as the name suggests, is a way in AWS, which is a cloud provider, that lets you auto scale machines, which means you go to a UI, let's say, and increase a number from 1 to 3. It starts 3 machines for you. If you increase this number from 3 to 10, it starts 10 machines for you. This is a great way to scale your application. And this will help you get over the problem of your application not scaling very well. Will it help you solve the other problem of remote code execution? Sort of. If every user gets their own machine, it doesn't really matter if they blow up the machine. They are not affecting other users. That said, you should still containerize your app a little bit if you're going with this approach, but generally not a big fan of this approach. Why? I will share very soon. Second one uses something called Kubernetes and container orchestration. This takes away the problem of scalability. This takes away the problem of remote code execution. Let's discuss how these two problems scale very well. First, let's discuss the cloud specific auto scaling solution. Pretty simple. If you have 3 people connected to your platform, you start 3 machines in your AWS, GCP, whatever cloud provider you are using. So each browser is connected to their own machine, and each machine has its own set of limits. This is a 2 CPU 10 GB machine, 2 CPU 10 GB machine. If you have a premium offering, if this person pays you $20 a month, then you can be like, okay, this one has 4 CPUs and this one has 20 GB of space, and you can pick and choose. Every user gets their own machine on the internet. This is similar to you just creating a cyber cafe and letting people remotely access machines rather than having a physical cyber cafe. For the people who don't know what a cyber cafe is, 10 years ago there were no internets back home, so there were physical places where there were 100 machines and people would come here and browse the internet. That's what a cyber cafe was. This is just a remote cyber cafe now. What do you mean by remote? Okay, bhai, somewhere out in the world, a bunch of machines are there and people can rent those machines. People can run their Replit code over there. First approach: if a new browser gets added, a new server gets added for them. If this browser closes itself after 10 minutes, this server also goes away. And that's how you auto scale. Harkirat, what about remote code execution? Well, if browser 2 does blow up the server, browser 2 does not have access to the machine they had anymore. So that's fine. And what if, Harkirat, they start to explore this machine? This can be an empty machine. You can have no code inside. So it's mostly fine for you to directly run their code here. I'm saying mostly fine, which means you should still, have, if this is the EC2 machine, have another layer, another mini computer inside that this user can access. So they cannot blow up the big machine. They can blow up the mini machine, which is fine. So ideally, you don't want them to access the complete machine, but even if they do, mostly fine in this approach. What are the upsides of this approach? Very easy to do. As I said, auto scaling groups gives you a simple UI in AWS. You go there, you increase the number of servers go up. You can also do this programmatically, which basically means if you have a Replit-like platform and someone opens a browser, all you have to do is increase the number of servers and assign the newly generated server to this user. And then as people come and go, your fleet of servers goes up and down in number. That's the easy approach. Provides you a way to securely run code. As I said, whenever a machine starts, maybe don't give directly access to the machine. Maybe start inside this machine, a small machine, what's called a container, which we will discuss what it is very soon. And then let the user access that container. Auto scales. The name itself has auto scaling group, which basically means auto scales up and down, and no port conflict. Every person has their own set of machines. If I start a process on port 3000 on my machine, other person can start one on their machine. The ports won't conflict. Compared to in the last approach, the original approach, there was a single machine, two people tried to run the same process on the same port, or a single different processes also on the same port, they would begin to conflict. One person would not be able to take the port. All right, those are the upsides. What are the downsides? Number one, boot up time. It takes some time for the machine to come up. You cannot be like, acha, the person opens the browser, immediately gets a server. No, it takes like 20 seconds, 30 seconds for a machine to come up. Can this be faster? Yes. You can use something called ECS, where you don't bring up machines, you bring up containers. What does ECS stands for? It stands for Elastic Container Service. What does elastic mean? It means you can bring up less number of containers, and containers are much faster to bring up compared to a machine. Harkirat, what is a container? What is a machine? A machine, you understand, a real virtual machine somewhere on the internet that you are renting. A container might be that there is a very big machine inside which you start one container, and if another user comes, you start another container. Another user comes, you start another container. That is why ECS will not really have boot up time as a problem. Generally also 20 seconds, 30 seconds, mostly fine. You can do a bunch of, ad hoc maths here. If you know, at a time only 20 people are on your Replit platform, and whenever you see a spike, the spike is only of 10 people. You have a warm pool of 10 machines always ready. What do I mean warm pool? I mean, if 10 people come, there were 10 machines sitting there idle. You just assign those 10 people here and then start 10 more machines, which take more than 20 seconds, but that's fine. No one's visiting them. So as long as you can predict your spike, what do you mean by spike? If a lot of people come together, if you can predict this, you can always have a idle pool of machines ready so that there is no boot up time. Whenever someone comes, you assign them to one such idle machine. So you can sort of get away with these problems. Not cloud agnostic. That is a downside. Not cloud agnostic means that AWS has its own autoscaling group. GCP has its own way to autoscale. So if you write the code once, if you write it for AWS, it will only run in AWS. If you write it for GCP, it will only work in GCP. You cannot have a single code base that runs both in an AWS autoscaling group and in a GCP, whatever autoscaling service that they have. And lastly, over provisioned servers. The biggest problem in this approach is user 1 has access to 2 CPUs and 10 GB of space. Maybe this guy doesn't need 10 GB of space. This guy only needs 1 GB of space. So you have over provisioned resources for them. You are not sharing resources amongst these fleet. You have not said, I am going to bring up total of 20 CPUs and total of 100 GB of space that all my users can share. You have said, I am going to bring up 1 2 CPU 10 GB machine for first person, 1 2 CPU 10 GB machine for second person. And so the resource allocation is very specific and strict. In the end, in this case, you have 8 CPUs and you have 40 GB of space. What if this guy needed 30 GB of space? This guy needed none, this guy needed none, this guy needed none. You have those resources, but you're not providing this guy with those 30. You're saying why you only get access to 20. Same for CPU. This guy might not be using any CPU. This guy might not be using any CPU. This guy might need access to the whole 2 CPUs. You already have those 2 CPUs. You are not able to provide them with it. This is why the biggest problem in this approach compared to the next approach, the container orchestration approach is, you have very strict and overly provisioned servers. A lot of times you might not need 2 CPUs and 10 GB. A lot of times you might need more, which is why it might be good to not have such strict restrictions on resources on these machines. Let's see how container orchestration fixes that. Kubernetes or container orchestration. You can sort of use them interchangeably, probably not. Let's understand what this service means. What is Kubernetes? What does it let you do? How is that better than this original cloud-specific autoscaling approach? All right, let's understand from first principles. What is Kubernetes? Why is it slightly better of an approach to follow than autoscaling servers? And how does it work under the hood? Before we get into why this approach is better, let's understand 2 jargons. Number 1, containers. Number 2, Kubernetes. If you need a deeper dive into this, I have a 2-part video on YouTube for like 2 hours where we deep dive into Docker. You can look at that video if you feel like going deeper. If you want a high level overview, I'll take you through both containers and Kubernetes. K8s is just a short form of writing Kubernetes. This and this mean the same thing. Let's kick things off with containers. What are containers? Let's try to build intuition for them. Let's say I have a Mac machine and I open 4 terminals in it and I start a Node.js process here, a Golang process here, an React project here, and a Rust project here. All 4 of these are running on this same machine, my Mac. They are sharing the file system. What do I mean when I say sharing the file system? I mean this index.js also exists in my file system. Same for this file, same for this file, same for this file. They can they can all access my machine, this Rust file. If some malicious code is written here, let's say, then it can access, my Node.js process database secret. Similarly, there is some malicious code written here. This guy can read my React project. The file system is the same. This was the first problem in our original approach. Okay, if this is my Mac machine and I let other people run their code here, I can let other people explore my file system, which is something we don't want. Here, containers come into the picture. What are containers? Okay, this is my Mac machine, but rather than starting this process directly on my machine, I am going to create mini computers. I'm going to create mini computer 1, 2, 3, and 4. And this will have its own file system. This will have its own file system. Same for this guy, same for this guy. They will not be sharing resources. Specifically the file system, if this JS code is malicious, it can only read all the file system code here. It cannot go to this other container and read the file system here. They have their own files, they have their own networks, they have their own place where you're running this code. Why is this good? As I said, what do we want in the end? Okay, people send their code and we run them. Where should we run them? In a mini computer. If this is your main Mac machine, start a mini computer for the person and let them run their code there. If there is some malicious code there, they can explore their mini computer, they can do whatever they want. You don't give them access to the main machine. That's the goal, right? So that is what a container is. A small mini machine running inside your big machine. And this mini machine has its own file system. It can do whatever it wants there. Cannot access the parent file system. Cool. It's very isolated. Another good thing about containers is they have their own network. What do I mean when I say they have their own network? Well, if you remember originally, or even if you look at the slide here, if I start, let's say a Node.js process, it's running on port 3000. I start a Golang process. It might be running on port 3001, 3002, 3004. All of these machines are using the network of my main Mac computer. If you don't know what ports are, a good refresher / a good thing to know is ports are a way for you to expose things to the world. If you want other people to, visit your backend service or to get back HTML, CSS, and JavaScript from your React code, is when you expose things over a port. And what is the problem? If you remember in the original approach, port conflict was the biggest problem. Okay, 2 people cannot start React projects. If this person takes over port 3000, this person cannot take over port 3000. This problem also goes away inside a container. Each container has its own network. Each container has, let's say, his own 3000 port, its own 3000 port, its own 3000 port, and its own 3000 port. They don't share the network. And since they don't share the network, the first person can start a React project here on 3000. Second person can start here on 3000. The ports will not conflict. A good question you might ask at this point is, if the code is running here on port 3000, how does this person access it? What does it tell the Mac machine? Where does it go? Localhost, what port? How does it know? Localhost 3000 should go here or should go here. And here you can use something called, this won't be a problem for a long time, so don't worry too much about it. But you can basically expose something on port 3000 here and 3000 here. And on your Mac machine, you can be like, anything that's comes on port 2001, go to the 3000 port here. Anything that comes on port 2002 on my Mac machine, go to this specific containers port 3000. You can create what's called a port mapping to expose this and this over the internet on different ports, even though this guy took the port 3000 and this guy took the port 3000. They took the 3000 port, but the external process that is accessing the machine doesn't necessarily need to hit 3000. It can hit 2000, and you can tell by 2000 of the Mac machine,
goes to 3000 of this machine. Same for this guy. If you want a detailed explanation of this, Docker video has a very nice section on port mappings. You don't have to understand port mappings at all here. The thing to understand is why containers are better over running your code raw on your machine like this, because each container has its own network. Each container has its own file system. You can isolate code very well. And that's what we want in the end, right? We want isolated containers where we run external code, which is why containers become an extremely important concept. At this point, you can almost build intuition as to how you can create a system like this. You might be like, Harkirat, I understand now. All that I have to do is ignore the slide for now. In my Mac machine, whenever a user comes, I will start their process in a container. Whenever a user comes, I'll start their process in a container, so on and so forth. Does that fix the problem, Harkirat? Yes. That is exactly what you have to do. You want to allow, as people come, you don't run their code directly here. You run their code inside an isolated environment, or you run their code inside a container. The question is, how can you do that? How can you start containers on demand? How can you, someone comes to your Repl.it page, you start a container for them to access this container. And then when they go away, you kill this container. How can you build a system like this? And the answer is using container orchestration. What does orchestration mean? It means, what does an orchestra do? There is a person in the front guiding everyone, right? So what does container orchestration mean? There is something that is orchestrating how and when containers should start, stop, so on and so forth. That is why Kubernetes is a neat approach to solve this problem. Can you do container orchestration without Kubernetes? Yes. You can use, you don't have to use a fancy container orchestration engine. In the end, what is this guy doing? It's just starting and stopping containers. You can do that on your own as well. This just makes it very fancy. We'll see the benefits of it later on. Cool. If you want to run multiple such containers and auto scale your servers, so the other point is, what if you want to run multiple such containers and auto scale your servers as well? I repeat, right now you have a Mac machine and you can totally be like, Harkirat, sorted. If someone comes, I will start a container for them and they will access this container. Other person comes, start a container. What is the problem? Remote code execution is fine, but what is not fine? Auto scaling. You are still not auto scaling servers. You can only have 10, 20, 30 containers at a point, right? At some point, your Mac does not have enough resources to support everyone. How do you auto scale? How do you start another server which can run the next set of containers, and then another server that can run the next set of containers? If containers go away, how can you stop this? And move all the containers that were present here to other machines so that you keep auto scaling up and down. That is what Kubernetes provides you extremely well. Let's see how. Container orchestration, Kubernetes. What if you could have a cluster of machines? I repeat, a cluster of machines. What does cluster mean? 3 machines, 7 machines, 2 machines, a bunch of independent machines. Could be a Mac, could be a Linux machine, could be a Windows machine, could be a Ubuntu machine, could be 3 Ubuntu machines, 2 Windows machines, 5 Linux machines. Does not matter. If you have a fleet of servers or a cluster of machines and describe in a single file how to run multiple containers, wouldn't that be nice? Wouldn't it be cool? I don't have to worry about if I have a single Mac or the auto scaling bit. What if I can just start a fleet of servers, be like, 10 servers are running, and then describe in a single file that person 1 needs a container 1 that needs to run Node.js, person 2 needs a container 2 that needs to run Python, so on and so forth. And then run some command on this file, and this single command would start a container here, here, here. The command would know, there are 4 machines we have access to. So it would distribute containers very well. Wouldn't it be nice? Wouldn't it be nice if that command was able to figure out, there are too many containers now. Let's bring up another machine. What if you could delegate all of this to someone? Number 1, starting containers. Number 2, auto scaling machines. There is a big difference. I repeat, big difference between what a machine in this cluster is and what a container is. They are significantly different. The machine is a big Mac machine where you could have 20 GB space and 8 CPUs. A container is a smaller space inside. I am running 4 containers here. Each one of them only has 2 CPUs and 2 GB space. So what do you want to scale up and down? You want to scale up and down machines. If there are a lot of containers that are started, start another machine. If there are less number of containers that are started, stop this machine and move whatever containers you had that are running here to different machines. All of this orchestration is handled by Kubernetes. Let's see how. What if you could have a cluster of machines and describe how to run multiple files in it? Let's look at one such file. Okay, what if you could write a file like this that says, okay, bhai, start a React container with 2 replicas. What does a replica mean? Number of containers you need like this. If you have 2 people on Replit right now that are running React, you want your file to contain, okay, bhai, 2 React containers, please start. And then secondly, let's say there's a node process also running. There's a person who's accessing Node.js on the Replit website. You can be like node container, 1 replica, and you can run a single command. Okay, Kubernetes start, let's say. And then what will that command do? That command will figure out, okay, I know I have 4 machines. I know I need to run these 3 containers. Let me put 1 container here, 1 container here, 1 container here. Boom. You gave away all this pain to someone else. That is what container orchestration lets you do. You can also not just write a file. You can also write code in JavaScript, code in Golang that looks like this. You can be like cluster.start React tab, cluster.start React tab. If you run this function in, let's say, Python, in JavaScript twice, Kubernetes will figure out that haan bhai, there were 3 containers originally. This person ran these 2 commands. They want to add 2 more containers. It will add 1 container here, let's say 1 container here. It will try to, of course, distribute resources well. In the end, if all the 4 machines have 1 container, 5th one, it will put on another machine. A single machine can run multiple containers. So wouldn't that be nice? Okay, you just run a single line of code and then Kubernetes figures out how to start a container, how to stop a container. It figures out if this goes down, it needs to bring it back up, so on and so forth. That is what container orchestration lets you do. Some Kubernetes jargon. If you want to do container orchestration now, start machines, run a command, start a container, you need to understand some jargon. Let's understand that jargon one by one. Number 1 is nodes. I hope that's clear. The real machines that you have, the Mac machine, the Windows machine, the Linux machines that actually run your mini computers, your containers, are called nodes. You could have a single node, you could have 10 nodes, you could auto scale these nodes. Okay, bhai, if a lot of containers have been started, start another node. If a lot more happen, start another node. You can have a min and a max. Okay, bhai, my Kubernetes cluster will have minimum 2 computers, maximum 20 computers. And based on the current number of containers, I will scale up and down. Or based on the current average CPU, I will scale up and down. If the average CPU that is being used is 50%, then I'll scale up to make sure this value goes down. If the average CPU that is being used is 0% or 2%, then you can scale down so that this number goes up. That's how you can just bring up nodes in Kubernetes. So what's the first thing that you need if you're running a Kubernetes engine? You need nodes where Kubernetes will actually run. You need machines where you will start your containers. Pods, the second one. Is it self-explanatory? If this is your machine, the mini computer that you run inside, the container that actually has the React workspace, the Node.js workspace for the end user, that is called a pod. Can you call it a container? Yes. But the Kubernetes jargon is you are starting pods, you are stopping pods. The mini machine that's running here is called a pod. All right. Next up comes some mildly advanced concepts, services and ingress. If by the end of this video, you understand this and this even okay, it means I've done a decent job. It took me a really long time to understand when do you need services, when do you need ingress, what's the difference between them, when you use one over the other. Services and ingress control how your application is exposed. How can people access your services running inside the pods? How can people reach your React application? How can this is your final node inside which you're running a container or a pod. How can someone access it? How do they know that if I go to x.repl.it, this is the place where I need to visit? How can people access your services running inside these pods? How does a user that has created a REPL reach the container where their code is present? In the end, even Replit and us today, we are going to have multiple nodes. And inside these, we have small mini containers. A single node could have 100 such containers. How does Repl.it make sure if you are on a certain REPL, you're able to reach that specific container that you're running the code on? Let's see this in action here on their website. Let me open Repl.it in 2 different tabs. Let me create a REPL here. Let me create, let's say, a Node.js REPL here, or maybe let's just do React twice. So a React REPL here and a React REPL here. I'm going to run both of them. Right. If I start the first REPL, I can see my output here. I can see the React application compiled and I can visit the website. The code of this exists where? It exists in app.jsx here. If I click on the new tab, it takes me to this page. Notice the URL. It says some random string.picard.repl.dev. Similarly, if you look at the other one, this is another React project. And if I open this in a new tab, it has a different ID, .pcard.repl.dev. Means they're able to somehow, even though this and this might be small pods running somewhere, they're able to let me reach that pod by hitting this URL. If you understand DNS resolution a little bit, maybe you don't. And if you don't, feel free to skip the next 1 minute. Let's see what this URL points to. What is the underlying IP this guy is trying to hit? If I go to my terminal and I run the command ping space the very long URL, it says this URL points to this IP right here, 35.266.206.236. Makes sense. Let's look at what the other URL points to. Oh well, the other URL also points to the same machine. How is it happening? Okay, this URL and this URL that are both different URLs but point to the same machine give me different outputs. Here I see the first application. Here I see the second application. How is it routing me to the right service or the right pod based on this URL? That is what we need to understand next. All right. That is what services and ingress let you do. Let's see how. Services and ingress let you expose your pods. You can either expose them on the internet, or you can let other people access your pods, as in one pod access the other pod. Each pod can have an associated service. So first of all, why do you even need this thing called service, Harkirat? If a pod starts, why isn't it automatically exposed? Why doesn't it have an IP associated with it? When it starts, why do you need to specifically create this thing called a service? And the answer is, you might be aware of only full stack applications. So you might be like, okay, every application that I start, be it a front end or a back end, they're usually exposed over the internet. When I start the front end, it is available on x.repl.it. But there are a lot of applications that they don't necessarily need to be visited by someone, that don't necessarily need to be exposed over the web. For example, if you're training your ML algorithm, it's a very heavy task that's happening. You don't need it exposed anywhere. You don't need anyone to visit that specific node. In fact, you want to protect that node as much as possible. So Kubernetes by default, when it starts these pods, it does not let anyone access them. I repeat, you cannot hit a URL by default and say, okay, let me reach this specific React project. If you want to expose it, you create a service. You attach a service to React or the specific pod, and then this service has an IP that you can visit. When you create the service, it gets an associated IP. Now you can hit this React application. Similarly for the other application. In fact, even if you want to expose them to like data between each other, if you want to expose one pod to the other pod, if these two pods also need to talk to each other, if this guy needs to hit this guy needs to expose an internal service. So you can have like an internet facing service like these two. Or you can have an internal service. Okay, I am exposing myself, but only to my pods, not to the outside internet. That is what services let you do. Whenever you create just a pod, it is not exposed. No one can visit that pod from the outside. If you create a service, is when you can expose it for other pods to visit or people from the internet to visit. That's what a service is. A service can also load balance across pods. If I create a service, I can attach it to multiple pods. I can be like, bro, this is a new service that is going to hit either this node or this node. It will load balance between each of them. For example, if you use Kubernetes just to deploy a basic backend application, in this case, you won't have an architecture like this. You will not have different instances and different services. You will have a single service. Okay, bhai, this is my IP. This is what I will put in GoDaddy. This is what I will put in my DNS registrar. Okay, bhai, google.com or whatever is your website, let's say harkirat.com, points to this DNS. This request will reach this service, which will load balance across these two nodes. So it's not necessary that you use load services. Every node needs to have an attached service. You can also be like, bhai, this is the service which will load balance across multiple nodes. Cool. That's what a service lets you do. Let's go through the Replit runner and see how they expose services. What do you think they do? I just showed you. What do? They are like, this is the first pod. This is the second pod. You can reach the first pod by hitting this URL. You can reach the second pod by hitting this URL. But both of them pointed to the same IP. I just showed you when I ran ping here, the first one also points to this IP. The second one also points to this IP, which means they are both pointing to the same service. I repeat, their architecture does not look something like this. It isn't like they start a node and then create an associated service. And then the first service has one IP, second service has different IP. We just saw they have a single IP. So they're doing something like this. They have created multiple pods, but they probably only have a single service which has an IP that we have pointed these two URLs to. I've said both this URL and this URL point to the same IP. And then somehow Kubernetes is figuring out if the URL 1 is happening, go here. URL 2 is happening, go here. That is what might be happening. You might think approach 2 is the right approach. You might feel like this is what they do, and they do this. But services don't let you expose path-based routing. Ignore the first line here, it's a little confusing. Services don't let you do path-based routing. If you expose a service and it gives you an IP, it will not be like, okay, if the request is coming from here, this URL, I will go to pod 1. If it is coming from this URL, I will go to pod 2. It does not let you do path-based routing. They will load balance, but they won't let you control where the request goes. If you create a service and if you hit it from different URLs also, which you can do, you can register, both n1.google.com and n2.google.com, so on and so forth. You can expose all of them to point to the same IP. A service won't let you do path-based routing. If request comes from this, go here. If request comes from this, go here. A service will not let you do that. That is where ingress comes into the picture. How can we do path-based routing? And the answer is, what should be present here? What do we want in the end? We want, irrespective of this request might come from various URLs, either pod1.repl.it. If you look here, it's exactly what it is, right? A very big ID .pcard.repl.it.dev. What is the other one? A very big ID .pcard.repl.it.dev. So it's going to come in a URL that looks something like this. pod1.a_constant, pod2.a_constant. And based on this initial part, you have to either go here or here. We need something here that is able to hit either this service or this service. You cannot put a service over here. What is the thing that you put here? And the answer is ingress. You might ask, Harkirat, whatever is present here, why can't it go directly here? Why do we need a service attached here and a service attached here? And the answer is you do. This node can be exposed to, as I said, over the internet or locally by a service. Same for this guy. Whatever is present here says, bhai, I will route to either service 1 or service 2 or service 3 based on the path. What do we want? We want path-based routing. And this specific thing over here cannot do path-based routing directly to a pod. Maybe it can actually, I don't know. Probably not. If it can, it sounds like an anti-pattern. Most probably it cannot. If this thing cannot do directly a pod, it needs a service on the other side. Okay, bro, I will either hit this service or hit this service. Cool. That is what this yellow thing needs to do. And what is this yellow thing? It's what's called an ingress controller. Not exactly an ingress. We'll see what an ingress is and how is it different from an ingress controller. But what is the thing that is present here that is doing path-based routing? It's something called the ingress controller. What does ingress mean? Ingress means incoming traffic. What does controller mean? Controller means controlling where the incoming traffic comes. That's what ingress controller means. So the final architecture should look something like this. You have various URLs that point to the same IP, just like Repl.it. And these requests reach an ingress controller. In the ingress controller, you create an ingress. Ingress controller and ingress are different. Ingress controller is, okay, bhai, I will tell where to go, but whoever wants to tell me, okay, if the request comes from pod1.replit.it, create an ingress with me, register an ingress with me. Tell me, okay, bhai, I am starting a new pod. If you ever receive a request from pod1.repl.it, please hit my service. Someone needs to tell the ingress controller that, okay, bhai, I am sitting here on the side. This is my service. Please hit me if pod1.repl.it comes. And how do we do that? Through an ingress. We create an ingress that has all of this written. What are these constructs here? What is this? What is this? What is this? What is this? We'll see how you can create them. We'll see later how you create a node, how you create a service, how you create an ingress, and how you create an ingress controller. But the architecture looks like this. Incoming request goes to ingress controller. And whenever these pods started, they registered themselves with the ingress controller by creating an ingress. They told the ingress controller, okay, bhai, here is my details. If a request is coming here, send it to my service. Same for this guy. It says if the request is coming here, send it to my service. This is the final architecture, which has nodes, the thing that is finally running your application, where your actual node index.js code runs, which has your file system, which has your network. A service that exposes this internally, an ingress that every service that is being brought up is attaching to the ingress controller, which is receiving the incoming requests. If you see it from the top, if you go to this URL right here, if I go to this specific URL, what is happening? Incoming request is hitting an ingress controller, which is doing path-based routing. And where are all of these rules defined? If the path is this, go here. They're defined in all the ingresses. So basically, Harkirat, if someone comes to Repl.it, you are creating 3 resources for them. You are creating a node, a service, and an ingress, and that is correct. Anytime, we'll see the code later on. Anytime a user comes, we create these 3 resources for them. All right. One extra thing to call out is, okay, bhai, this actually is nothing but a service and a pod only. In the end, the ingress controller that I'm talking about, that hits, that I've written in yellow here, is actually nothing but a service and a pod. It is a service that is exposed. But since services cannot do path-based routing, the control from here reaches here, and the pod checks, ki, acha bhai, what is registered with me? Acha, pod 1 is registered here. Let me send it to pod 1. So ingress controller is nothing special. The ingress controller is effectively just another service and a pod. And this pod is actually the thing that's doing file-based routing. And why did we have to do that? Because services by default cannot do path-based routing. If we did not have this fancy thing here, if we just had a service, that service won't be able to route here or here, which is why we had to do this fancy thing. I would call this whole section fancy, which has what? An ingress controller, which is nothing but a service and a pod, and a bunch of ingresses, which is what all services are present. And where should a request go? If the request comes here, it should go here, comes here, should go here. That is what ingress controller and ingresses mean. Cool. They can exist in different nodes as well. So you might look at this architecture and feel like, acha, okay, this is a single node where this can happen. If you have multiple nodes and there's a process running here and a process running here, there's a pod here and a service here, pod here and a service here, this ingress controller cannot reach here. The answer is no, it can. As long as it is in your cluster, this ingress controller could be on any node of the cluster. It will be able to discover the other services irrespective of which node they are on. You don't necessarily need a single node. You could have multiple nodes, and the ingress controller will be able to route traffic to anyone. Given all this information, can you guess the final architecture now? Can you guess what happens when I go to Repl.it? This screen though does nothing, shows you a bunch of things, ignore. When I click on create Repl, Node.js, do this. This also probably does nothing, copies things from S3 somewhere. When I reach this page, what happens? When I click run, how do I reach the right place? When I'm in this shell, how am I interacting with the right terminal? Can you guess the architecture now, given all this information? Take a pause and try that. I'm going to proceed, but if you want to think it yourself, try to create a diagram. Try to think, okay, this should be probably the ingress controller. Here is where the request should go. Whenever a user comes on this specific page, what do you think should happen in your infrastructure? What do you think should get created so that now this user has a resource in our cluster? And what do you think should happen when the user goes away? You should delete some resources. Can you, given this information, guess this a little bit? Pause. I'm going to proceed and share all the steps that I take to create my infrastructure that auto scales, is protected, and users can reach the right services based on the path of the URL. Step 1, start a Kubernetes cluster and set some auto scaling policies on the node. This is the simplest bit. This is not specific to Repl.it. Any application if you create that is deployed on Kubernetes. You can deploy a simple front-end application if you want on Kubernetes, probably don't. You can deploy a back-end application. You can deploy a machine learning application. If you want anything that needs to have container orchestration, you can use Kubernetes. Step 1 remains the same. Starting a Kubernetes cluster which has some auto scaling policies on it. Okay, if the load increases, increase the number of nodes. Load decreases, decrease the number of nodes. I repeat, nodes are auto scaled based on some policies. You can write, if the CPU usage is more than 50%, I will increase this blue baksa. I will increase the number of nodes. If it goes below a certain point, I will kill some nodes and move the containers from these nodes here. Kubernetes does all of this heavy lifting for you. Step 2, attach an ingress controller to the cluster just one time. This is a one-time effort. As people visit your website, go to your website, you don't have to do this step again and again. But for once, you have to attach an ingress controller. You have to be like, bhai, whenever the users finally come to the website and they're going on these weird URLs, that request will be handled by this ingress controller. I will create one of this one very big, huge ingress controller will be created, which you can create in like a single command. You don't have to, understand and create a pod or a service. We will see how easy it is to just simply run a command and start an ingress controller. Once you do this, you are not yet live. You have not yet told everyone to visit my Replit website. You are preparing. This is the preparation stage. Okay, I have this. I have my nodes, the auto scale. I have an ingress controller. Step 3 is you point your DNS to the IP of the ingress controller. After you start this, you can get its IP. Okay, haan bhai, this incoming IP for this is 1.2.7.3, let's say. And then you go to godaddy.com, you go to googledomains.com, you go to squarespace.com, and you say, okay, by star.repl.it, or in these guys' case, whatever the URL was star.pika.replit.dev. You go to Google domains and you say, bhai, this thing points to this 1.3.7.3 IP, this IP right here, so that all your subdomain requests are going to this IP and are being handled by this guy right here. Harkirat, in the end, I will have only 20 pods. Why am I pointing star? Why am I pointing everything there? Because you don't know what the name of that pod will be, right? It could be a random name. So you're saying everything go here. If the user tries to hit pod1.repl.it, and if there is a pod1 that exists, request will go there. If there's no pod1, request will dump whatever. But you will have to create a wildcard entry. You will have to say, this domain is gone then. At least this subdomain, if you've bought a domain on GoDaddy or wherever, this subdomain's whole job, pika.repl.it, is sole purpose is कि भाई multiple ID will come here. I need to point or take the user to the respective pod. So we're done with 2 steps. Step number 1, just to recap, create the cluster. Step number 2, attach an ingress controller. Step number 3, go to godaddy.com. The interface will look something like this. This is my Google domains. I have the URL gptflock.com, and I created a record here कि star.gptflock.com should point to my ingress controller. This IP, I'll show how you can get it later on. But yeah, I got it from Kubernetes. It's the IP for my incoming ingress controller. I put it here. Cool. Step 4. As people start to create repls, if someone comes, now you're ready to go. After you've done these 3 steps, you're like, anyone can visit my Replit website. And then as people come, Start Repls. You start a pod, a service, and an ingress for them. When people come to your website and someone says, I'm on this specific workspace, I now am coding for the next 2 hours. For the next 2 hours, you start a node, attach a service to it, and start an ingress so that all incoming requests to that specific pod can be routed to this node so that the user can, start to play with it, run their website, visit their website, go to the terminal. If they change a file code in their, Replit, if they start to type things, they are reaching this service that is effectively eventually putting it on S3, things like these. We are creating multiple containers, but unfortunately creating a container isn't enough. You need to route to that container, which is why you have to create a service as well and an ingress as well. Harkirat, why ingress again? Why not just service? Because every service has its own IP. If you have 2 pods in the end, both of them will have their own IP. What will you do? How will you go to GoDaddy and say कि अच्छा भाई pod 1 dot whatever your website is, go to this IP, and then pod 2 go to this IP. You cannot do that dynamically for every domain name of yours. You can't keep going to programmatically to. You can do that. That's a very ugly and anti approach and bad approach of dynamically creating DNS records on GoDaddy.com. Ki haan bhai, I started pod, I will start service, I will point p1.100xf.com to this service. You can do that. It's a very ugly approach because this step takes a lot of time. DNS propagation can sometimes take 2 hours, 3 hours. You don't want your user to be stuck on the website, which is why you need only once the DNS propagates, ki bhai star.repl.it points to this IP, and then you have an ingress that does path-based routing. Ki incoming request, go here based on the first part of the domain. Hopefully that's clear. The 4th step, which is as people come to your Repls now, create 3 things for them: node, service, and ingress. As people go away, so there was a single person, you started one, another person came, you started another one person left, you stopped all the resources. You stopped their ingress, service, and pod. They are gone now. Whenever they come back, you can restart their ingress or like create a fresh ingress, service, and pod. So that's how you create and destroy nodes. So Harkirat, in the end, if there are 1,000 people currently live on Replit, all 1,000 of them have 1, 2, 3, all 3 of these. Yes. I mean, I don't know what Replit's infrastructure is. Of course, if they don't use Kubernetes, they do use something else. Whatever they use, they have mini infrastructure running for every person somewhere. For if there are like 1,000 people currently live on Replit. Probably step 5. Clusters will auto scale based on the policies you add. This is just that, okay, if you have 1, 2, 3, 4, 5, a lot of containers coming in, you can just initially, in step 1, whenever you're starting the Kubernetes cluster, attach some auto-scaling policies, and then your number of nodes can just go up and down as your number of containers increase. Your policy can be like, if there are more than 100 containers, then at least 10 nodes should be there. If there are more than 100 containers, then you should start another node. You can decide the rules based on which your nodes auto-scale. But that is just something you don't have to worry about. Thankfully, your cloud providers worry about. If you're using AWS, if you're deploying your Kubernetes cluster on AWS, in AWS you can create what's called a node group. Another jargon I'm introducing, you don't have to know. But like you can basically tell Kubernetes the minimum number of nodes I need is 2, maximum number of nodes I need is 10, and keep going from here to here based on the current number of containers, based on the current number of these 3. There are more number of these 3. Of course, these 3 will exist together, right? Whenever you start this, and this together. Otherwise, you don't need just a container won't be able to do anything. Sorry, just a pod. Just a service won't be able to do anything. You need all 3 of them. Based on number of these triplets, you can auto scale up and down. Lastly, you don't really need Kubernetes for what you're doing. You can use other container orchestration engines. The nuances will remain different. They might not have the concept of a service. There might be a different way to do service discovery there. What is service discovery? Basically discovering where should your request go. So every container orchestration engine will have its own way to discover services, own way to start containers. You can use any. We're using Kubernetes, probably the most fancy one. Kubernetes gives you a bunch of things that we don't need today. So Kubernetes is not just start these. Kubernetes is also monitor these. Okay, bhai, if I told you to create a pod and if it went down, Kubernetes can also restart the pods. We're sort of using that today, but basically Kubernetes gives you 10 different things that we're not using today. And yeah, if you want a subset of those skills, you can find another container orchestration engine. Kubernetes is probably the best one to go for. Cool. What have we learned? Containers, container orchestration. What are some advanced things that are not needed today, but Replit does use? I'm going to very quickly take you through them. And then if you want, you can improve our solution at the end and add three things. Although these are something that even Replit added after a long time. If you go to Replit's GitHub, you will see that they recently introduced Nix. Before that, they also used Docker to create containers, or like more specifically to do something called package management. Recently, around last year or so, whenever, I don't know the timeline, they moved to something called Nix, which is another high-level jargon to know. Nix lets you do what are called reproducible builds. Harkirat, what does that mean? Basically means, since Replit needs to support a lot of stacks, Node, Go, Python, so on and so forth, these keep on getting added. An easy way to describe what you need in a single file is by using Nix. And reproducible builds basically mean, as long as you have the single file, it will just work and reproduce the same output on a Mac machine, on a Linux machine, so on and so forth. So it's a better way to do package management. We've not discussed package management too much now because we're using the old approach of how Replit used to work, which was a single big Docker file. If you go to their GitHub, let me open it real quick. They have a project that is now archived that says base Docker image for the Replit evaluation server. Before, they used to use Docker and had a base image. Okay, bhai, this specific image, I don't know the complete details, but if I had to guess, they had a single very big, what is an image here? A snapshot of a machine which has Node also, which has Python also, which has Rust also, so on and so forth. So they had a single such very big image. And now they have moved to something called Nix that lets you do the same thing in a cleaner fashion, lets you only get the dependencies you need or packages you need. And yeah, they have a video, I'll probably link it on the top right with an eye icon and in the description, where one of their engineers goes through why Nix is really cool, how you can bring more packages to your machine because now these guys use Nix. Second thing is something called network volumes. So yeah, one thing you will see very soon when we go through the final architecture, you will see we have a machine which is a node inside which we're starting a pod, and this pod we will restrict some resources on it. We'll be like, bhai, you can maximum use 2 vCPUs and maximum use 20 GB of space, something like that. Now this 20 GB in our approach right now exists on this node, which basically means if this node has 200 GB, we can safely say it's very easy. You can start 10 different containers here, because each container will maximum use 20 GB. You can actually start 100 containers here, because realistically not everyone will be using 20 GB. People will probably be using 1 or 2 GB. So you can commit to them 20 GB, but realistically not everyone will be using 20 GB. So even with 100 GB you're good enough, because this guy will use 1 GB, this guy will use 2 GB. You can theoretically tell them you can use a lot, but realistically not everyone will use 200 GB. Even in the worst case, if you have 200 GB on this node and you tell everyone, bro, maximum 20 GB, you can start 10 containers. A better approach here is something called networked volumes, which means that bhai, the storage of a node doesn't exist, the storage of a pod doesn't exist here. It exists somewhere else in a very big store, somewhere else, which is called a network volume or network file system, NFS. And this way you can give a user much more space. In fact, Replit gives you 250 GB because they don't use the space of the node. They say, by you go here, we have a very big elastic store of storage. You can use 250 GB. Again, realistically, this guy won't use 250 GB. So this does not mean if there are 10 nodes here, they have 2500 GB stored here. This probably is like an elastic store which goes up and down. Final place where they store your code and everything else does not exist on the node, it exists outside, something you can improve upon. Number 3, caching dependencies, which basically, if you go to a REPL and if you're on a, let me give a quick overview of this. Basically, if you're on a node and you start a pod here, the pod needs to start with some base data. Okay, dude, this pod needs to have node plus, oh my pencil died, but this pod needs to have node and Python and some specific packages. So you can cache them on the node. You can be like, bhai, yeah, it's not working. You can be like, that specific node needs to cache the Node.js library, so that as we start more and more pods, they come up very quickly. Caching dependencies is just a way to start your pod very easily, because that's something you want to optimize for. As more and more people come to your platform, you want to start their pod as quickly as possible. So you want to cache as many things that they're reusing on the node itself, so that the node isn't hitting the internet and getting the Node.js image from there and starting the pod. It should immediately get it and start it. And if you explore Repl.it's file system, you will see they have a mount. If you don't know what a mount is, like they have on every machine, they have all the Nix dependencies or a cache of all the Nix dependencies that they need, which is why they can almost immediately bring them to your machine. This also they take you through in this video where they talk about how and when they introduce Nix. All right, cool. Let's get down to my solution. I've explained everything. I'm just going to reiterate the architecture, show you a bunch of auxiliary extra services. We understand the basic thing that needs to happen, but we need some extra services. So I'm going to share it from the top to bottom, the final architecture, and then we will look at the code. All right. Next up, I want to take you through the file structure, the extra services other than the core logic that I've discussed that you need to finally be able to do everything inside a Replit app and not just, start containers. There are a few other services we need. So let's get into my final proposed approach. We have 3 services and a Kubernetes cluster. So number 1, you have to start a Kubernetes cluster. Number 2, I'm going to introduce 3 services. 2 of these services don't need to exist on the cluster. They can exist outside. They can be on a simple machine. These runners, or what I'm calling runner WebSocket server, they will of course be deployed in the Kubernetes cluster. These are the things that need to, start up whenever a user comes and whenever the user goes, they need to be brought down. Simple HTTP API, we'll see what that does, can exist independently, does not need to be part of the cluster. Orchestrator also does not need to be a part of the structure. What it is, I will discuss very soon. The simple HTTP API, the first thing I wrote here on the left, let's see what it has to do. It has to help just initialize the REPL. Basically, when the user is on this screen and they click on the create REPL button, it needs to do the same thing we did in the first part, which is copy over the base image, the base code from S3 and put it to a certain other key or a different place in S3 from where the user will finally access the code, from where the container will pull the code for the first time. We need a service that runs on this button click. We also need authentication services. Replit has 10 different things. All of that does not need to necessarily reside in this core WebSocket server. It can reside outside, which is why I'm putting it in a separate simple HTTP server. Right now, in our case, it only has to do one thing or support a single endpoint. When a user clicks on create REPL, copy over the base image over to some specific section in S3 and tell them good to go, we're ready, and you can start to visit the REPL. Runner service, or more specifically, this runner WebSocket server right here. This is the one that needs to have all those things that we talked about. If this is a node, and when the user comes on REPL, we start a pod here. The code that exists inside this pod, the code that the user finally talks to as they type things in, and the code that backs it up to S3, lets user run npm run dev, all that code will reside in this runner service, call it execution service. And what is it? It's almost the same as the WebSocket service we built in the last section. WebSocket service that this specific REPL can hit to save all of their edits there, to call npm run dev here, to access the terminal here in this container. All of that is exposed via a WebSocket server or a runner service. So hopefully this is clear. This runner service is the same. This section right here, the thing that autoscales, not autoscales, but thing that needs to come up anytime a user visits your REPL. We'll see what the code inside does, but what does it need to support? It's basically what happens. So ignore the what needs to support. It basically is what happens after the user starts your REPL. We need to start an independent runner for them, and while it starts, the user sees the loading screen. So this code is the pod that is starting, the code that exists inside the pod that is starting while the user is on this loading screen. While it says REPL is booting, what is booting? A small container. And what is going to be stored there? This specific code that we write in the runner service. And lastly, a service called an orchestrator. It can be an HTTP or a WebSocket service. We are going to stick to HTTP. And it needs to support just a single endpoint, which gets hit when the user is on this loading screen. When the user is on this loading screen, they hit the orchestrator and tell them, I am ready to go. Please start a pod for me. And what does the orchestrator need to do? Hopefully it's self-explanatory. It's the orchestrator. It needs to tell the Kubernetes cluster, okay, bro, start a new pod. There is a new user here waiting to edit their environment and run commands, start a pod here with the runner service. So this guy's job is to just start and stop pods. This does not run any of the code that backs things to S3. This does not run any of the code that, takes the edits from the files here and puts it here. That code resides here. This is the orchestrator. Its goal is just to start pods here and then even stop pods as the user goes away from this specific website. And lastly, so let's just visually understand what happens. When the user comes to the website, they tell the orchestrator, okay, I want to start a Node.js container, or I want to start this specific REPL ID. And what does the orchestrator do? It starts a runner and of course puts the code from S3 inside the runner. We'll see where this happens and how you can, in a very clean fashion, while you're starting the runner, pull the S3 code here. But what does it need to do? It needs to prepare the environment for the user. It needs to be like, acha, the person is here. Let me prepare the environment for them. Let me start the runner. Let me pull the code from S3 and put it here. And let me return to the user. Okay, bro, here you go. You can access your final runner on this URL. You can hit this specific URL and then you are connected directly to the runner. I have started the things for you. This guy's goal is just to start the service and let the user know your service has started. There you go. This is the URL you can hit, whatever pod1.repl.it, and you can create a connection to this runner and do your thing. Once you get back the runner address from the orchestrator service is when you directly connect to the runner. Of course, you go through the ingress and then ingress controller and then all that jazz. But effectively, what is happening after you go through all of those hops of ingress, container, and ingress, you reach the runner. You have a WebSocket connection directly with the runner service that we had created. And now you are sending your edits to that guy. He's sending it to S3. You are telling it, bro, npm run dev, please. It's starting your port. Once it does start your process, you are accessing it on, whatever, a.repl.it. So that is what the high level architecture is. Let the user edit a file. So as the runner starts and you initiate a WebSocket connection, as you edit a file, as you add more code in there, you send that code over to this service, which backs it up to S3, changes the things in the file system, and then eventually, whenever you start a terminal, it starts a virtual sudo terminal inside the pod, so that whatever commands you're running are running on the pod and not on the node. You have access to the file system of the pod, of the small machine, not the node that is running it. And you start a sudo terminal also where you start it on the same pod so that you can, blow up the pod, do whatever you want. You cannot blow up the machine that's running it. And lastly, of course, relay keystroke commands. If you have started the terminal, then through the WebSocket server, you will send the commands to this terminal. Terminal will respond back. And that is how you can run npm run dev here, start your React project for that matter. Then once the React project starts on a specific port, you can visit it again through the ingress controller and then the ingress, so that by the end of it on pod1.repl.it, you can reach your specific runner and visit this website, look at the HTML code there, or if you're starting a long running backend process, then hit the specific endpoint and get back the backend code. Cool. Step 7, in case the user ever leaves, stop the pod, stop the ingress server. I've not done this in the code yet, but it should be very simple to add. You can either add a background service that regularly cleans up any pod that hasn't been visited in a while. You can also have a different service. You can also self-destruct. Okay, if the user disconnects and stays disconnected for over 3 minutes, the pod self-destructs itself and the services. You can also have another process that's monitoring it and making sure if the user has left, you clean up the resources. I have not done that in the code, I'm telling you upfront. It should be very easy to add, either a background service or just when the user leaves, whenever this WebSocket connection breaks, after 1 minute, self-destruct. And lastly, why is this secure? What have we changed since the last approach? What is the biggest thing we have changed? We're executing remote code in a pod. If this is my Mac machine, and even if I'm running it locally, whatever sources I'm starting in a pod. If you can blow up the pod, go ahead. You cannot blow up my machine. You cannot read any sensitive information on my machine. Pod has restricted permissions. The pod can only be accessed in certain file locations. You cannot stop some parent processes, things like these. It's a very restricted permission that the user has on these pods. Pod has resource limitations. Even if the machine is a 250 GB machine, you can say whenever I'm starting a pod, the max CPU that this can consume is, let's say, 2 vCPUs. The max space that this can take is, let's say, 10 GB, even though the node might have 200 GB on top of it, so that a single user doesn't exhaust all the resources on your node. And lastly, pod has its own network, so you can start multiple processes on the pod. They won't conflict with other pods. Every pod, this is the node, every pod will have its own network, your ingress controller, and then requests can go from here to here. This can also have something running on 3000. This can also have something on 3000. It's their own network that they're running things on, and not the parent node network. And why is this scalable, Hakirat? Well, as I said, starting a new runner is as simple as starting a pod. Of course, the auxiliary, ingress, service, all that jazz. As the CPU usage goes up, more pods can get added. Hakirat, where have we written this logic? This happens in your cloud provider. If you use AWS, you can over there say, bhai, I'm creating this node group, and the minimum number of nodes here is 2, the maximum number of nodes here is 20. Go up and down based on certain conditions, CPU, length of a queue, so on and so forth. As the CPU usage goes up, more pods get started. All you have to do is increase the number of nodes in your cluster, which also you don't have to do manually. You can just tell AWS, bro, please go from here to here. And all you have to do is start pods, basically. Node autoscaling up and down happens yourself. I hope you understand the difference between a node and a pod now. Pods is what you need to start. Increasing the number of nodes, decreasing the number of nodes can be delegated to AWS or whatever cloud provider you're using. A few callouts that might feel like good to haves, or might be good things to clean up. Number one, user can inspect your WebSocket code. This is not good. What are we doing? We said, okay, bhai, if this is, go back a bit. We said the orchestrator starts a runner, and this runner is what you directly connect to, which means this pod has some code that you can read. You can try to restrict the user's access to that folder, but in the end, it's running in the same file system. You can also do fancy things like, run it in a different container. You can have a parent container, 10 different things you can do. But right now, the connection between the user and the runner, this runner has your, WebSocket code that has the logic of, if you send the images, put them in S3 here and then put them something. So put them here in the file system and put them somewhere else. If you start a terminal, then start a terminal here. All this logic is in a file. It's a JavaScript file that the user can inspect, delete, all that jazz. Of course, a user can do whatever they want with their pod. In the end, as long as it doesn't affect our infrastructure, we're fine. It's their pod. They can do whatever they want. If they want to blow it up, they blow it up. You are a good service, and you just restart it for them. Cool. That's the other sort of ugly thing to fix. And lastly, user can still reboot your machines. You can do that on Repl.it also. If you run reboot on Repl.it, it'll restart the machine. Your terminal will stop, or the container will stop. It'll restart. You have access to the same file system again. You cannot trust the user in this case. You can just restrict them as much as possible from taking advantage of your resources. You can make them, bhai, you only have access to 2 CPUs. First, go to our $20 a month plan. Then we will give you access to 5 CPUs at a time, so on and so forth. So you have to put restrictions at some point. And the user can still reboot, do bad things. Nothing you can do about it. All you can do is, protect your core infrastructure so that the user doesn't, reuse it. If you go to Replit today and they give you 250 GB of space, you can put 250 GB of your movies there and then access them whenever you want. These are always use cases or anomalies that will come. You have to, figure out your way around them, ban users, all that jazz. A few advanced things that Replit does, and I haven't done yet. Number one, they use Nix for reproducible builds. This is something we have not used yet. We're using just Docker, or more specifically, using base Docker Node.js images. Or if you really want to go extremely optimal, use an Alpine Node.js image, which is like a very small Node.js image. If you're starting a Python process, start a Python image, or have a single container, just like I showed you, Pygot, the thing that Replit had, that has all of your, Node, Replit, Python, so on and so forth, and start that specific container. We don't use Nix for this. They use Nix to do what? To get dependencies on the machine, to get the Node.js runtime on the machine, to get the pip library on the machine, so on and so forth. You can use Nix. I don't have too much experience with it. I only heard about it when I was going through a podcast between the founder of Replit and a few people. So from there, I heard about it. It's extremely apparently very fancy. And I want to try it out somewhat. I did not in this video. Network mounts to allow users to get to. So as you want users to have more and more space, you should not, if this is your node, give them space on this node itself. You should create a network mount, probably an elastic network mount, so that their storage happens somewhere else, and they can get access to more storage because this guy auto scales up and down. This node space you can't really take up and down. And lastly, Repl.it doesn't allow the user to directly connect to the pod, but most probably relays information via WebSocket server. Yeah, I'm not sure about this. This is purely me speculating based on, looking at the connections and seeing what's happening, which is, okay, what we do is, if this is the node and this is a pod inside, and this is your browser, you directly connect to the pod. Of course, you go through an ingress, but in the end, you're connected to some code that is running directly in the pod. I'm not sure if that is what Repl.it does. But my guess, and this could totally be wrong, it's probably wrong, I don't know. Basically, I don't know yet. Okay, they relay this through another server. They don't let you ever directly connect to the node. I could be wrong. Well, that's my speculation. So you talk to the server through some other, parent service. That's all the callouts. Now let's get into the code base. Let's understand how I build this. Let's go through, all the steps from top to bottom. Let me take you through all the services that I've written. All right, I'm going to now start doing all the steps from top to bottom and share the code with you, how I wrote this. How can you try the same thing locally? We'll not be using we'll be using paid services, but you can get credits for them for free. There is this cloud service called Vultr that you can create a Kubernetes cluster on. You can also create on AWS, GCP, doesn't matter. As I said, it's cloud agnostic, but Vultr gives you $250 of credit. I will try to find a referral link thingy that they give to YouTubers. I should disclose upfront. Okay, you will get $250 of credits. And if you ever buy something from Vultr on the same account, I will get max $250 of credit for that. And if it's not my link, it's someone else's YouTube link, but you should know and have this information. Okay, if you buy $250, or if you use the referral link, you will get $250 of credits. And if you ever pay, the YouTuber will also get $250 of credit. With that, after you've created an account, you will see something like this. I also used a different YouTuber's sort of affiliate link to get $250. And I use this for some cohort server. Right now I've brought down all the services here. I'm going to start a Kubernetes cluster. So if I go to products, and you can pretty much see the same thing on your side if you've signed up on Vultr. If you click on Kubernetes here, it'll let you add a cluster. Cluster is one thing I never introduced, but I hope it's self-explanatory. A bunch of nodes in which you're running your, Kubernetes cluster is what's called a cluster. So if you click on add a cluster, it'll let you give your cluster a name. I'm going to call it Repl.it, and the version of Kubernetes you want to run on it. Now Kubernetes is what? In the end, it's just, a software that's running on all of these machines. So the version of that software that you need, if you need high availability firewall, we don't need any of that. The location in which you want to start the cluster, I'm going to select Mumbai, India. The number of nodes that you need. So for now, we're having restricted number of nodes, only 3 nodes, but it's very easy to auto scale them. I'm sure Vultr provides it some way. I don't see it here on the dashboard. AWS provides it. Pretty sure Vultr will provide a way to auto scale nodes up and down. Right now, I'm selected a exact set of 3 nodes that my Kubernetes cluster will have. And then make sure the costs are less than $250 so that you can run it for a month. Click on deploy now, give this a label, call it nodes, and deploy. This will, number 1, start 3 machines in the Mumbai region for me. Number 2, start running Kubernetes on them so that I have these nodes available that I can run various commands on, start services, start pods, so on and so forth. Wait for it to finish and then we'll go from there. All right. When this status changes to running is when you know you have a Kubernetes cluster running somewhere. If you click on it, it'll take you a page like this and it shows you have total 6 CPUs running, 3 different machines with 2 CPUs, total RAM, all that jazz. The way for you to interact with this cluster, the way for you to talk to this cluster, you need some authentication, some password. That file, that place where you can put all of these passwords is this configuration that you can download. If you click on this, it will give you a very big YAML file. For those of you who don't know YAML, YAML is similar to JSON, basically a file that looks something like this, where it has where my Kubernetes cluster is running, how do I connect to it, the name of it, all that jazz. This, if you share with someone, they can then, they have access to your Kubernetes cluster. So basically don't share this with anyone. I'm also going to delete my Kubernetes cluster before the video goes down, so you can't access any of my resources. Now that you have this file, where can you put this file so that whenever you're running Kubernetes commands, this cluster is what gets hit? Even before that, how can you run Kubernetes commands? How can you start a pod? How can you start a service? How can you start an ingress controller? For that, you need access to something called kubectl or kubectl, which is the command line interface that lets you talk to Kubernetes clusters, that lets you tell the cluster, okay, bro, please start a pod. So the way to install this locally is just Google kubectl install whatever machine you're on, and let's say it's Mac OS, then you can download this, put it in your path, just follow the instructions. I'm not going to go through this. By the end of it, you should either have a binary called kubectl, or you should have this in your path. So if you run the command kubectl, it should just run for you. For very simplistic purposes, have put it in a folder of mine. I have access to kubectl. I can now run commands using kubectl to start a pod, stop a pod, start a container, so on and so forth. All right. Given you have this, where should you put this VKE-311, this very big YAML file that you got, that you have your all your credentials to connect to your cluster? It's in .cube. It is this config file in the .cube folder. If you go to your root folder /.cube, inside this there is a config folder. Let me move this config folder to file to a different file, and then create a fresh config file, not config.txt, not config.js, not config.yaml, simply config, where I copy this and paste this code. This file .cube / the config file is where you copy over all of these credentials, so that now kubectl can talk to your machine. It knows that this is the server I have to talk to. Before this, I was talking to a different server, which is what I copied over to a different file, so that whenever I have a backup of that file locally, I can connect to that server. But for this newly created cluster, I copied over the credentials to config. Now, if I run a kubectl command, if I go back to the folder where kubectl was present, which for me is present here, and if I run the command kubectl get nodes, it tells me I have 3 nodes in my cluster. It tells me here, Kirat, you have a Kubernetes cluster. It is running these 3 nodes. They were started 4 minutes ago, 4 minutes, 3 seconds ago, 4 minutes, 3 seconds ago. If I run kubectl get pods, it tells me there are no resources. I haven't yet started any pod, which is why nothing is running. I can start more pods if need be by running, a command, or more specifically something called deployments. We'll get to what those are. And yeah, if you're at this point, make sure you can get back nodes, make sure you can get back pods, and then I probably have to take you through some more Kubernetes jargon, specifically what are deployments, and then we will proceed. Either way, make sure at this point you have kubectl and Kubernetes running locally. You can connect to your cluster. All right, we're done with step 1 of creating a Kubernetes cluster. Step 2 is attaching an ingress controller to it. If you remember, the first place where all the requests come, which route the requests based on what the host name here is, was the ingress controller. Is ingress controller, is there only single ingress controller in Kubernetes? Do I have to do something like Kubernetes install or Kubernetes start ingress controller? And the answer is no. Ingress controller is a more abstract concept. The people who wrote Kubernetes said, bhai, anyone can create an ingress controller. It needs to do these things. And then many popular implementations of it exist. The one that we are using today is the most famous one, called the Nginx ingress controller. And the way to install this in your cluster. And what do I mean when I say install this? I mean start all of these services that you need. This service over here, this pod over here, a bunch of other things that this guy needs. Starting all of these in your cluster is what the Nginx, this installation will do. And how can you do it? There are various ways mentioned here. What you can do is, basically if you use Helm to install it, it'll run a bunch of commands for you. All of those commands or all of those configurations I have put in this Kubernetes /ingress controller.yaml. You don't have to understand this file, but this basically describes a bunch of things that you start in Kubernetes. A bunch of, let's say it says start a service account. It could say start a pod. It could say start a ingress over here, or it could say start a service over here. It probably might have a service here. Let's see. There you go. It says start a service here. What is this service? Most probably, I could be wrong, but most probably it is this service right here. It has been mentioned in a file. Okay, bhai, please start this service with this metadata, a bunch of other things. Start it on this port. This is probably it, because it's, as you can see, running on port 80 and port 443. So just this much code or this much YAML, which basically means this much key value pairs, which describe what happens, or what should start in Kubernetes. And this guy is clearly saying start a service, which is start this thing in the Kubernetes cluster is what this file has. Harkirat, it has 100 different things. Yes, it does. Harkirat, where is pod? We also have to start a pod. We have to start service. We have to start a pod. Where is the pod, Harkirat? Great question. Here, let me quickly introduce something called a deployment. What is a deployment? Harkirat? No, not Harkirat. You guys, when you have to start a pod, you can either be like, I am starting a pod. So you can be like Kubernetes start pod, and this will start a pod in your cluster. Or you can create what's called a deployment. Harkirat, what else can you create? You can create a service. You can create a pod. You can create an ingress. And what else can you create? You can create a deployment, which is nothing but you saying start a pod and keep this pod up. In case it goes down, restart it. If you just start a pod and if you kill that pod, it doesn't restart. If it dies down, it does not restart. But if you create a deployment and you say by start a deployment with one replica, which means one clone of this code, it will start a pod for you and it will monitor that pod. It is a deployment. I am going to watch this pod and if it ever goes down, I will restart it. That is the difference between a deployment and a pod. Usually, you will almost always start a deployment because you want my backend application, if you're using Kubernetes in the more, raw way for deploying normal backend applications, you want your backend has 3 versions or 3 pods running always. So we will not start a pod. You will start a deployment. You will not run 3 times Kubernetes start pod and then Kubernetes start pod and then Kubernetes start pod. No, you will say Kubernetes start deployment of 3 replicas of this specific pod. And what will it do? It will start 3 of them, and if anyone goes down, it will restart it. That is what this deployment is right here. Even when we write our code for starting things dynamically, we will not start a pod. We will start a deployment. Very subtle difference. Pod, if you start, if it goes down, it stays down. Deployment, if you start, if it goes down, it brings it back up based on the number of replicas that you have mentioned. This deployment needs to have 1 replica, which means it needs to have 1 pod that is always running. Cool. That is what this file has. It has a bunch of other things which are out of scope for today. Let's start a terminal and run kubectl. Go to the Kubernetes folder. Kubectl apply -f and ingress controller.yaml. If you run this command, it will start a bunch of these files for you unless there is an error just like my machine. Let's see. Namespace ingress not found. You have to create a namespace first. Namespace create ingress nginx. Create namespace. You first have to create this namespace. Here, what is a namespace? This should ideally be here. I should have included it here. Either way, run this command kubectl create namespace. This thing. Here, what is a namespace? Basically, is if you are starting a Kubernetes cluster, it might do 10 different things. Your big cluster might have your backend application, your front end application. So you say, by my backend, I am starting in a different namespace called backend. My front end, I'm starting in a different namespace called front end. Everything is still the same. When you start a pod, it still starts on a node. But when you attach it to a namespace, what happens is when you run commands like, kubectl get pods, you can specify the namespace. Okay, I want all the pods running in this namespace. And right now when I run this, what does it say? It says no resources found in this namespace. When you're starting this ingress controller, it is like, bro, when you finally deploy your applications and you're running this command to see what pods are running, I don't want my ingress pods to come here. I will start 10 different things. Let me keep them in a different namespace. So your default namespace, which is the thing that comes by default, the namespace where everything is stored by default, that doesn't get polluted. Logically, it does not mean you have a different partition here where everything is running, the ingress nginx partition and a default partition here. No, it's just a logical separation. Okay, whenever you run get pods, you get all the pods in the default namespace. If you run -- namespace nginx ingress nginx, you get all the pods in the ingress nginx namespace. And when you start nginx controller, it starts all your services in this specific namespace. So your default namespace doesn't get exposed. Your actual application, when you run this command, when you're exploring your thing, exploring your application, seeing what pods are running, the Nginx pods don't appear here. So you have a clean, whoever is debugging your application, seeing the pods running, doesn't see the extra fluff that this guy brings in. All right. Now run the command again, apply -f ingress controller.yaml. And as you can see, it says this created, it creates a bunch of things, creates a deployment, creates a service, basically creates these two things, a service and a deployment, which is, as I said, almost equivalent to a pod. It has created these two things and a bunch of other things. How can you explore them? You can run the command kubectl get pods -- namespace ingress nginx. If you run this command, it shows you 3 pods. This one is completed, this one is completed, which means they had a short running process. They ran something and stopped and ended basically. This guy is still running. This is your Nginx controller, ingress Nginx controller. This is this service, right? Or sorry, this pod right here. This pod is now running. How do you know? When you run kubectl get pods in this namespace, you get a pod is running. That is how you know you have this specific pod now running, and all you had to do was apply a single file, and did not have to go through a very tough installation process. We did not write any of this Nginx controller code. We just installed it. We just said whatever services we need, bring them on my cluster. My cluster now has all I need to route requests to my pods. The other thing, what do you want to check at this point? We checked that the pod is running. What other thing do I need to check? The service. Is the service running? And what is the IP of this service? If I find the IP of this service, I can go to my DNS provider and put that IP there, right? So next up, what is the command you think that I have to run? The command that I have to run next is kubectl get services namespace nginx ingress to pretty much get all the services running in the ingress nginx namespace. It has 2 services appearing here. One has this public IP, one has this public IP. Harkirat, which one of these is ours? The first one, which is running on port 80 and 443. This specific load balancer, if I copy over this cluster IP, is the IP that I need over here. Okay, the service of mine has this 1, 2, 3, 4, whatever this IP is. And I now need to go to my DNS provider, which is like whatever, Google Domains or Squarespace, and tell them कि भाई all requests going from star.xyz.com, please go to this specific IP because this is the IP of my ingress controller, the first thing where all the requests are coming. So what is the next thing I have to do? Copy over the external IP, not the cluster IP. Sorry, this was incorrect. The external IP, which means the exposed IP, the IP that's exposed to the world where people can hit this IP. In fact, if I go to my browser and run this, you can see it says 404 not found Nginx. Means something is running there. Nginx is running something on this IP. I have at least something deployed on the internet now. What do I need to do next? Go to my Google Domains account, wherever you have your, domain bot. So you have to buy a domain first. After you do buy them, I have a bunch of these here. Let me select a few random ones. For example, autogpt-web.com. Let me go to DNS here and add a record for star.autogpt-web.com to point to this specific IP, and do it for another one. I'll later on share why. You can also just go away with one such domain, but I'll share later why we have to basically, when you go to Repl.it and create a new REPL. After you've created the REPL, you need to connect to 2 pods, right? The first one is the WebSocket connection that we have directly to the pod. And the second one is when you do start the application, you have like a website running, an HTTP URL where you can hit it. I am separating them. You can also keep them together. If you did not understand this part, it's mostly fine. What I am saying is it might be good for you to have 2 domain names and not one, and point both of them to that IP. So let me do it for the other domain and then I'll explain a little bit more why I did it. The other one I'm going to pick is autogptcloud.com, unless this already has something. It does already have something. Let me see if I have another domain. All right, I have another domain name called peedcode.com, and I've pointed star.peedcode.com also over to the same external IP that I got from where? By running kubectl get services in that specific Nginx namespace, and the external IP, where if I go to the URL and hit this and see this, that specific IP I've put in two of my domains. How do I know that my DNS has propagated? Which means how do I know if every subdomain now is pointing to this IP? I can open a terminal, and similar to how I ran ping for the Replit URLs, I can run ping here as well. Okay, ping abc.peatcode.com, and it shows me 65.20.67.198, which is this IP right here. And let me ping the other one as well, which was autogptcloud.com. And now, as you can see, even ping random domain.autogpt-cloud.com points to some IP. So now I have two domain names, and more specifically, all subdomains of those domain names pointing to my Nginx controller. Now, what do I have to do? Move on to the next step. So let's see what step 3 was. Put the things in the domain. I already did it. Number 4. As people start REPLs, start a pod and service and ingress for them. So basically, the bootstrapping is done. Now we need to run the commands to actually start, an ingress, a service, and a node, given a user joins your REPL, given a user comes to your REPL. So now we need to look at all the services that I introduced, specifically simple HTTP API orchestrator service and the runner WebSocket service. This is the one sort of that we need to orchestrate. So let's see how you can do that next. All right, let's kick things off with the simplest service here, which is the simple HTTP API. This is similar to what we had written before, nothing new here. Let me take you through it really quickly. The folder we're looking through is the good code folder, and here there is the init service, which I've basically named this simple HTTP service because it initializes the REPL for you. If you go to index.ts here, you will notice what I do is I expose a single /project endpoint, which means the user will send you a REPL ID. Okay, and this is the ID of my final REPL, and this is the language I want to support, Python, Node.js, whatever stacks you support. And then you copy over the S3 folder, or in this case R2, doesn't matter either way, from the base folder where you have the base of that language, which basically means if I go to R2 here, if you see REPL/base/Node.js, it has just two files, index.js, package.json, package.log.json, which has like very basic code that the user starts off with. I copy over that code to code/that REPL ID, which basically means over here, REPL code/, you will see I have like a bunch of projects already created. So I've copied over the base project there, and then eventually this updates as your project updates. But I hope you get the idea. Okay, you copy over from base/that stack over to code/ whatever the ID of your thing is. If you want to see it in action, let me quickly start this specific service. So init service. Let me also start the front end. And if you go to the front end here and it gives you a random ID, you can change it if you want. Select the stack. I'm going to select Node.js. And if you click on start coding, the request goes out. If you were actually inspecting it, the request would go out to that service. If you look at the logs of the service, it tells you something is up, address is already in use, which means I was already running it. I'm probably running it. There you go. I was running it here. And here, as you can see, it logs, okay, copied over from base Node.js index.js to this place right here. Word person was the name of the REPL. Word person. That's where the user came also. All the other services are down, which is why you don't see like the main REPL here. But I hope you get the idea. Okay, now if I go back to Cloudflare, refresh this page, I can actually see the base code over here. That's what the init service copied for me from base to here. As you can see, it has index.js, package.log and package.json. If you want to explore more, you can go over to this copy S3 folder, which has all the logic of copying things from here to here. And there's also a small bounty in case you feel like winning $25. Go through this code, fairly simple, just gets all the files there and runs a s3.copy, which copies one object to the other place, and then finally returns project created. When the front end gets that, what does the front end do? It redirects the user to /coding/ Repl.it equal to whatever. And here is where we do the actual pod creation and the other things that we have to do, because when the user has created the pod or created the REPL, at that point, you don't really need to start any pod. They've just created it. It's just created an entry in the database, put something in the S3 store. When the person reaches this page, which could be right now, or could be in the future after 10 days, is when you need to start a pod for them. So now let's look at the other services that we have more specifically. Let's kick things off with the runner WebSocket service, because a lot of code is repeated here from the original project. We'll go through this and then finally we'll see how the orchestrator is able to orchestrate the runner. But first, let's quickly go through the runner. The code is pretty similar to what we wrote in the last one, so pretty much haven't changed anything. But let me take you through the runner next. All right, the runner code is present here in the runner folder. If you go to source/index.ts, you will see it looks the same. Only we haven't exposed an HTTP server. If you remember the original code, if you go to bad code/backend/index.ts, here I had initialized the WebSocket server. I had also initialized the HTTP server. I don't need to initialize the HTTP server anymore, because what did this guy have? This had the /project endpoint, which we've already moved to a different service, the init service. So we only need to support all the WebSocket endpoints, which basically is the same as this bad code that we'd written originally. So if I go here /index.ts, if I go to init WebSocket, you will see that it has the standard on connection. Oh, this also has one small difference. But again, get the REPL ID. The way it gets the REPL ID is a little different. Now it gets it from the host. When the user comes on, worldperson.xyz.com, it gets it from here. In the original approach, we got it a different way. What else? It does not get things from S3. This one's super important. If you remember, if I go to bad code/backend/source/ws.ts, here I would run this. I would fetch the S3 folder and bring it in memory, right? And here is where I would run npm run dev. Here I don't do that. Why? Because if you remember, I mentioned back when I was explaining it, okay, now when we start the pod is when we pull the S3 image here. We don't need the application logic to pull it. We don't need, okay, when the pod has been created and then the user creates the connection and then we pull the code from S3. No, since during pod creation, we know that this pod is being created for this specific REPL. When the pod is being created is when we can pull the code from S3, so that whenever the user connects to you, they immediately, are able to do things on it. They don't have to wait for the code to get pulled from S3. Cool. That is why the other difference here is I'm not fetching the S3 folder locally. It is already there. We'll see where. And then everything else is pretty much the same. Init handlers, user disconnects, we don't do anything right now. Eventually what you do here, the pod should self-destruct over here. Fetch dir gives you all the things in the directory. Now again here, where are we storing all the code? We're storing it in /workspace. Now every container has its own file system. I don't have to. If I go back to the original implementation, where were we storing everything? We were storing everything in temp/REPL ID / the code base. We needed the temp folder will have all the REPL's files. So in this REPL ID, I will store something. In this REPL ID folder, I'll store something. But here, every pod has its own file system, which is why I can put all the code in the /workspace folder. I don't have to worry about, /workspace / this REPL ID code is here, other REPL ID's code is here. The other difference here in this ws.ts file is we are storing all the code where in the /workspace folder. Can you put it somewhere else? Put it wherever you want. Put it in the /app folder, put it in the /dev folder, put it in the /worker folder. Depends on you. For me, when I start the pod, when I create the pod, is when I tell S3, okay, bro, please put everything in /workspace, because this is where the WebSocket server will pick and edit and put things on. So that's why, that's what I've used here. Everything else is the same. This gets the directories, this gets the content. This lets you update content both in memory and on S3. This lets you request the terminal from the server and, actually have access to this /workspace folder, all that jazz. Cool. Yeah, so I don't think I have to go through this again. It's the same as the backend code here. If you look at the file structure, is pretty much similar because it does the same things, only this was running on my Mac machine and this code runs inside a containerized environment in a small container. This is done, this is done. What is left? The code to actually orchestrate the container. The code that will run when I'm on this screen, and if I refresh this, whoever comes to my main REPL page to edit their code when it says booting here, a request needs to go out that actually starts the container. If you remember from the slides, the orchestrator's goal was, pen died again, but the goal of the orchestrator was whenever a request comes through an HTTP layer or a WebSocket layer, for our case, it's just a simple HTTP request. It needs to start a runner, copy over code from S3 into the runner, which is the next slide right here. And then, let the user know that the thing has started, and then the user can go from booting to actually show the user all the files here. Cool. That's what we're discussing next. The most easy to understand code, like not a lot of lines of code, but very hard to, if you've not done Kubernetes before, slightly hard to chew the syntax here. How did I start the ingress controller here? I said, bro, there is a YAML file. If you go to Kubernetes / this thing, it has a YAML file which has all that you need to start. You need to start a service account. You need to start a config map, so on and so forth. Don't know what this is, don't worry about. We need something similar. We need a file that looks sort of like this. If you go to orchestrator simple /service.yaml, it has a file, which if you look at it, says start a deployment. And if you scroll down a bit, it says start a service. Scroll down a bit, start ingress. Is that exactly what we needed? If you remember here, what all did we started? If you go back to the slides here, anytime a pod comes up, what all do we need to start? We need to start ingress, service, and node. We need to start 3 things. And that's exactly what this guy says. Start an ingress, start a service, and start not a pod, but a deployment. But as I said, pretty similar, not interchangeable, but you get the idea. This will start a pod with one replica, which means one pod it will start. Let's try to understand the syntax a little bit more, but if this is the first time you're looking at Kubernetes syntax, it might be a little confusing. This isn't the only way to start a deployment and start a service. You can also run commands like, kubectl start deployment and give all of these arguments here. It's usually easier to put it in a file. So you just run a command to apply the deployment rather than, remembering what all the flags are in a CLI. Cool. I have this file. I know whenever user comes, I need to start these 3 things for them. Let's go through them a little bit, slightly quickly. This guy says start a deployment, give it some metadata. This is the spec for it. Create one replica. Ignore what a volume is. Init container. Focus here. When the pod is starting, before it starts, something called an init creator. Init container is what you can start, which basically is before the pod starts, run this code. And what does it say? Copy over code from repl/code/service name. You will see the service name all across the file. This will eventually be replaced with the REPL ID. So don't worry, service name doesn't exist in S3. It will eventually, before you actually apply this, all of these will get replaced by the REPL ID, which is why you don't have to worry about, this service name being here. What does the init container in our case does? It copies over things from S3 to /workspace. It's exactly what I said, right? Now our container, while it is starting, is getting S3 stuff from S3. It's not the application logic. It's not the runner/source/ wherever the WebSocket connection was initiated. We don't copy it here like we did originally. We now in the YAML itself say, okay, before the container starts, copy over everything from S3 over to this container, and then give it some environment variables based on your AWS secrets so that it can actually reach the AWS server and copy. And then lastly, the containers that it needs to run. In our case, what is the container that it needs to run? You can actually run multiple containers inside a pod. In our case, it needs to just run one. And this is where the image of that container is. I'll show how the code that I sort of wrote here in the runner reached 100x devs /runner docker registry. But if you basically go through the Docker file here, while I created the runner, I also containerized it and pushed it to the Docker registry on 100x devs /runner, which is why, I can simply say pull the image from there. If you don't understand this, basically when your runner starts, it needs to know, I need to start with the Node.js background installed, Python and pip installed, Rust installed. You can push all of these images onto Docker Hub. Again, you might want to go through the Docker video if you want to understand this better. But basically the runner service that I have containerized it. I have created a single image of it and pushed it on Docker Hub. If you actually go to dockerhub.com, which is similar to GitHub, but for like images. And by images, I mean, place which has your code as well as your file system as well as Node.js, all these things. So this is the 100x dev / runner container, which has the code of what? Of the runner, which is why I simply say by start a container which has all of this code, and this code it pulls from hub.docker.com /100x dev / runner. And I say expose these two ports. This is where my WebSocket code runs. This is where my runner code runs. And this is if the user ever runs npm run dev and wants to expose their React project, it will be exposed via the port 3000. This is what the deployment has. Okay, when I'm starting the deployment to reiterate, first copy over everything from S3 to a workspace folder, and then start this specific image. And how does this image exist on Docker Hub? I containerize this runner app and pushed it to Docker. How can I do the same? Pretty simple. Just go to the Docker video. I show how you can push things to the Docker registry. Service is slightly simpler. I want 3001 exposed. I want 3002 exposed. If someone hits 3001 on this specific services IP, then it will target this specific container or pod, which in our case is, this will all get replaced with the Repl.it, but the high level is this service will send data where, or hit, if someone hits this service, if someone hits this specific service, oh my pen isn't working, but you get the idea. If someone hits the service above, the node above, the pod where I'm running that specific code is where the request should go. And how do you describe that here? You say by selector service name. Anytime a request comes to this specific service, forward it to this service name, which is present here in the deployment. And this specific deployment is referenced by this service name. And open these two ports on it. Lastly, ingress. The white thing over here. Three things we had to start. The white thing over here simply says, if a request comes to service name dot firsturl.com, forward it to port 3001. If it comes to service name dot secondurl.com, forward it to 3000. That's how the ingress sort of, there are two. If it comes from x.harkirat.com, the request goes to the WebSocket server, which you send the terminal commands to, so on and so forth. If it comes to x.harkirat2.com, it goes to port 3000, which is running my backend application. We'll see all of this very soon. All right. Now, once you have this specific service.yaml, this is just a single file where I've put everything. The actual code that orchestrates all of these things, the actual code that starts all of these things, is written in index.ts right here. If you go to orchestrator simple /index.ts, it's less than 50 lines of code. Now, what does it do? It says it first imports something called Kubernetes /client node. This library lets you talk to your Kubernetes container. It lets you start a service there, start a deployment there, so on and so forth. As I said, you can totally run kubectl start deployment, or you can totally be like a kubectl apply -f your YAML file, or so basically this, or you can use a Golang library, a Node.js library that lets you talk to your Kubernetes cluster. That's what we are using here. And we've exposed a /start endpoint, which pretty much says, bro, anytime the user wants to start a container, start the three processes, read and parse the kube YAML file. Read this specific file right here where we had written all of the code, the file that I showed you, and then parse it, which basically means, find the three sections from it. The first section, the deployment section, the service section, and the third one. And then iterate over all the sections. And then based on the kind, either start a deployment or start a service or start the ingress. That's it. If you write this much code, you might want to read through the read and parse kube YAML. There's also a bounty here, which actually reads the whole file and then uses the YAML library, which lets you parse YAML files. And then it gets all the three sections of the YAMLs. This part's important. Replaces service _ name with Repl.it. These two lines of code makes sure when you get this code here, replace service _ name, the thing that I put everywhere, with Repl.it. This is something more abstract called templating. We've basically templated this file. This is the template of whoever wants to start it, and whoever wants to start it, please replace this with your specific Repl.it. If you really want to build a more cleaner service, you can actually convert the file YAML file into a Helm chart. And when you do this, you'll understand what Helm is and how this specific use case is perfect for Helm, where you have a template that you want to use across various pods. Okay, cool. Hopefully this is clear. If not, you have to go through the code a little bit here. But what is it doing again? Anytime start gets called, which means the user has reached this page right here. The user has, if you look at it, if I'm at this page, if I look at the network tab, if I refresh, where does the request go out? The request goes out to /start, localhost 3000 /start, which is this endpoint right here. Request comes here, and here is where you start all of the three processes. Cool. That's pretty much it for this section. Let's start this right here. Let's also start, the other services, which is, oh, by the way, like this automatically finds your kube config, so you don't have to put anything here. If you don't put any special credentials here, it will by default pick up your default kube config and connect to your server. So it pretty much good to go. The next thing you should do is, replace all of your credentials here with, your actual AWS key, AWS secret, all that jazz. And once you do, is when you're good to go. Number one, start your orchestrator service. So npm run dev. Number two, start your init service. So go to another terminal. And start the init service. Number three. Oh, it's already in place. Where is it running? Okay, init service already running. I have init service running. I have orchestrator service running. Runner we have already deployed to Docker Hub. We don't have to run it anywhere. It'll be the thing that's orchestrated. These are the only two services we need to run. Then lastly, let's start the front end and see if it actually does what it's supposed to do. So if I go and yarn dev, if I open this, am I missing something here? Are we done? Let me quickly replace my AWS credentials here. Let me go off screen for a second. All right, I replaced my AWS credentials in service.yaml. You should do the same. Where does this file exist? In orchestrator simple /service.yaml. Also, one thing I forgot to change was the actual URLs that I had pointed in my DNS. So if you remember, if I open this terminal, there was peatcode.com and there was autocloudgpt or autogptcloud.com. I replaced both of these here as well as in my front end code. So if you search through the code base for peatcode.com, you'll find I changed it in one more place. Basically, I create the socket connection now to Repl.id.peatcode.com and no longer to like a hard coded URL. And similarly, whenever you actually view the user iframe, the iframe that actually has your final React application or Node application, I pick it up from Repl.id.autocloudgpt.com. Cool. Because of these were the two that I pointed to my current cluster or my ingress controller. I have to replace them here as well as in my front end code, and then we're good to go. Let me again show you what I am running. I'm running the front end. I'm running the init service. I'm running I'm not running the orchestrator. Let me run that. Cool. So I have the orchestrator running locally on port 3002. I have the init service running locally on port 3001. And I have front end running here. If I go to the front end now, let me click on, let me just go through the flow once and then let me show you all the things that are happening. If I come here, I can create a random URL or it just gives me a random ID here. Select the language. I've only put Node.js in our Docker file for now, so Python won't work, but it's pretty easy to replace the Docker file there and either add everything in your Docker file that includes Node and Python, or have separate Docker files and then start the right container based on what is the kind of coding environment that the user is in. If I click on start coding, booting happened very quickly, which means most probably it just worked. Loading. And then after a few seconds, something might have crashed, most probably. Oh, it took really long. Why? This is the first time we're pulling the Docker image on the nodes. Now that we have it, it'll be much faster. What has changed? what do you see on the screen? Oh, it happened in the first go. Beautiful. I see the code that was present in the copy of S3 that I made. It's present here. Can I update it? Yes, I can. When I update it, does it update in my final container as well? As you can see, where am I? I'm in /workspace. If I cat whatever index.js here, you see the updated code has reached my container. Probably 99% has reached S3 as well. We can open and confirm. How do I see the output? I will have to start the Node.js process, node index.js, first npm install, and then node index.js, and it's started this code right here. If I click on see output, I can see hello world, whatever here. If I change this to hi from the container, if I rerun the process, if I click on show output again, I see hi from the container. So pretty much works. Basically, you have access to a smaller mini computer now, rather than having access to the whole node. If you explore this, you will see the workspace folder has all the code, and you can reboot this if you want. But what will this reboot this time? It will reboot just the container and not, I guess the command is this, but like you can find a way to exploit this basically. As I also said, it also has my WebSocket code somewhere here. If I really want to explore wherever we are pulling wherever in the Docker image we pull the Docker. So if I go to Docker file here, and here if you look at it in /code is where I had put all the code. So if I go to /code here, and we can restrict the user, whoever is accessing the terminal, to not be able to go into this folder. I haven't yet, which is why the user can explore your WebSocket code, your runner code, which is not great. They can also stop this, look at all the processes that are running and then stop that specific process. There's a lot of things that the user can do. But since all of that happens inside a container, your nodes, other people aren't affected. Your security isn't breached. Or is it? I mean, we probably have the AWS credentials here. So yeah, you should almost, do we? Probably do. cat.env, yeah, probably do. We do. So one very big call out here, we have the AWS credentials in the /code folder. So you should 125% restrict the user from getting into this folder. Or what you can do is, let me give another sort of thing that you can do is start a different container that has all the WebSocket code. So what you can do, do this. This is a better approach. Let me take you through the YAML service.yaml. If I go to the top here, when I was starting, the 100x devs runner, I should start this as a separate container and then start another container along with it. This second container is where the user will run their code. This first container is where we have the WebSocket server. The user will connect to this WebSocket server. The WebSocket server is what will send, it can basically talk to this other container, and that way your user container has none of your code. Your user, whatever this, simple Node.js image or node :latest main runner. And now what you can do is this container and this container can sort of talk via a socket, and your end. Let me go through this on the iPad. Oh, the iPad seems pretty down. Let me go through it on Excel later on. Basically what is happening is, what you can do is, when you start your pod, inside the pod you can start two different containers. C1, which has your real code, which has your WebSocket code. You get the idea. This has the WebSocket code. And then this one, the other container, is what the user has, the user code. The user talks to you through this proxy. They talk to you through C1, but they can only sort of run terminal commands in C2, and C2 does not have any of your code. They send the command here, which sends the command here. Harkeet, how can you connect these two? You can connect two containers, make them communicate via sockets, 10 different things, ways you can, make a connection from here to here. And by connection, I mean just forward requests from here to here and then forward back responses from here to here. That way the user only has access to C2, which does not have any of the user code. Right now, C1 has the user code, and what is the problem? The problem is, since the user code is here, the user can explore the .env file, which has your S3 credentials, because this is putting things on S3. You can also restrict the user from coming into this folder, but ideally just keep them as separate folders. I think that's the more cleaner approach than doing this. The only problem there is two containers are sort of talking to each other. So pick and choose. But basically what we have here is a little insecure. So let me just mention that somewhere here. Might have exposed my credentials, but that's fine. I'll delete my AWS credentials. There you go. So I'll probably mention here user. All right. So whoever does this gets $100 bounty. Second one is very easy. This one is slightly harder, but the first one seems like a more elegant approach to me. Okay, on the file system itself, it's not present. The second one you have to just make sure the user that is having access to, by user I mean whoever is the user here, that you're giving access to. Basically, the end user doesn't get access to root. They get access to a new user, and the new user does not have any read writes on this /code folder. That way, they cannot read and write code here. Cool, good. What else is left? That's pretty much it. If you want to look at the requests that come and go, I mean, one thing that's left is clean up. So that is another thing you need to figure out. Okay, the pod actually self-destructs. If you want to explore all the pods that are created, just run a few kubectl commands. Kubectl get pods, and as you can see, the new two inside person, whatever was the name of our container, this thing right here, we have a pod running for them, we have a service running for them, two inside person, we have a ingress for them, two inside person. So these three were started from a Node.js process. And if you want to look at all the requests that go out, first you're on the landing page, and let me restart this. If you look at the requests, the first request when you're on this page goes out where? It goes out to the init service /project, which copies over everything to S3. Then you get redirected here. Then the request goes out to /start. And as you can see, initially the socket server isn't up. The container is still coming up, which is why these requests fail. And then when the socket server actually starts, we'll see when that happens. Again, this is a little, oh, there you go. I went a little quicker this time. Is when, the socket connections are now open, and now you have access to your mini machine. That here is your code, here is your terminal. Do whatever you have to do with it. All right, cool. What else is left? Not really. I think I've covered everything. Yeah, let me know how this was. Let me know if you do any one of the bounties. There are some simpler bounties here, and this one is a complex one. Whoever does this one, I'm not even sure this is a good approach. The reason I came to this approach was because when you go to Repl.it, if you go here to Repl.it on any one of the repls, and if you click on inspect, refresh this page, if you look at the WebSocket connection, which they do, of course, create a connection to their server. So this is the service where your WebSocket connection is made, and it does not have an identifier in the URL, which tells me, and I could totally be wrong here because the identification might happen based on the route. But my guess is they have a separate WebSocket fleet of servers which relay things to the main container, and the main container. So if I type something here, you can actually look at all the messages. There are like too many messages that they send. I don't know why. I don't know if it stops protect what data is coming. Data is also pretty hidden in binary, so you can't really inspect what happens when you run something here and go to index.js and try to run this. I spend a lot of time here. But my guess is their WebSocket server, whatever layer is forwarding things to the container, exists separately, because I tried a lot to find the code here, but I couldn't. But yeah, that's my guess basically. That's one thing you should implement if you want to mirror them one-to-one. Cool. That's all for this one. Let me know how this was. Let me know if you want something else, and let me know the pace. I know this was a little hard if you did not know Docker or Kubernetes, but either way, let me know how the video was. Let me know what else you would like for me to build. With that, let's end it. See you guys in the next one. Bye bye.